Hello, everybody. Thanks for the nice introduction, and thanks for inviting me to be part of this summer school. So I am Francesco Orabona, and this lecture will be online convex optimization and its surprising applications. So what are the aims of these 3 hours? I will try to provide you an introduction to online convex optimization. And the slides will be almost rigorous in the sense that the theorems will be correct. The proofs will be also correct. I will skip some details here and there about convex analysis, but you can be sure that the main message is correct. And I will also try to convey you connections between online convex optimization and a number of other fields that are known to people that works in online convex optimization, but are typically unknown to people outside. Now, unfortunately, I don't have nice pictures to show you. I don't have geometric intuitions or nice diagrams. I have a lot of proofs, but they will be short. Each one of them will be only one slide, and not because I basically summarize them or I reduce them. This is really the proofs that I will show you, and I will show you proofs because it's the only way to do to design online learning algorithms. There is no other way, unfortunately. And so ideally, when in 1 week you will forget everything about this summer school, you can still go back to these slides and use them basically as a cheat sheet because all the theories is correct, all the proofs are correct. I also want to say that most of this material is based on the sort of a draft of on an online learning book that I'm constantly writing and updating. Some of my recent blog posts and of course some recent papers. Okay, so this is an outline of the lecture. I will first introduce you the problem of online convex optimization and what we mean by regret. And then I will mainly focus on 2 classes of algorithms, that is online mirror descent and followed regularized leader. Then I will briefly talk about parameter-free online algorithms. And then I will tell you something that I believe, by the way, this is the most important part, the connections between online learning and other fields. So I will show you how to use online learning to do non-smooth, non-convex optimization in an optimal way. I will show you how to use online betting to prove concentration inequalities. And I will show you how to use online betting also to prove pack-based bounds. Okay, so let's start. So what is online convex optimization? So it's basically a game that you play against an environment. So in each round, the algorithm has to output a vector x of t in some feasible set v. Now, after you make your prediction, the environment will reveal you a loss, lt, and you will pay the value of the loss in the point that you predict. Just after that, you basically receive some kind of information from the environment. For example, you might receive the gradient, or you might receive just the value of the loss in the point, and you basically update your internal knowledge so that you will be able to predict the next point, xt plus 1. Now, there are a couple of things that I want to stress. You choose x of t before looking at the loss, okay? And so this is the difficult part of the problem. We don't make any assumptions on how the losses are generated. So differently from classic stochastic or batch optimization, where in batch it's always the same functions that you are minimizing in each round. Where instead in stochastic optimization, we assume that the losses are coming IID from a certain distribution. Here, the losses can be generated in any way, possibly even in an adversarial way. So possibly the environment is trying to push the algorithm to pay as much loss as possible. So what is the aim of this game? We want to minimize basically the cumulative sum of the losses that you pay. And so you want to minimize over all the choices of all the vectors that you made throughout the rounds. However, I told you that the losses can be generated in an adversarial way. So this quantity can be as high as possible. And so it doesn't make any sense to say that I want this quantity to be small, but instead it makes more sense to say that I would like this quantity to be small compared to another term. And this other term is the cumulative loss of a fixed point u. And so we call this quantity here, this difference, the regret after capital T iteration with respect to a competitor u. And I want to stress the fact that it's important that we keep the dependency over U here, instead of saying, I would like to compete with the best U in my set, because the best U might not exist. So we don't assume that the best U exists. And this is particularly important because I will consider a lot of times linear losses, and the set V is just the entire RD, and there is no minimizer for linear losses over an unconstrained set. Now, we will say that the algorithm is good in the sense that it has no regret if the average regret with respect to any competitor U is going to 0. And so why this is a good objective? Because basically it says that on average, over time, the performance of the algorithm will converge to the performance of any fixed competitor. Okay, so we are doing as well as the best competitor that knows the futures, because U is chosen with the knowledge of the entire game, while the algorithm knows only the past in each given point. Okay, why we should study online convex optimization? Why we should put ourselves in such a difficult framework? Because there are a number of problems that are intrinsically online. So, for example, if you know what is learning with expert or learning with banded feedback, these are basically just special problem for online learning. And so, online convex optimization, it's basically a strict generalization of this class of problems. But it's also generalized the problem of the standard problem of batch and stochastic convex optimization. And most of the time, I want to stress you, like 99% of the time, you can study the problem of stochastic and batch optimization in the online learning framework. And then just at the end of the proof, you can basically say, oh, by the way, the losses are stochastic. And you don't lose anything if you do the analysis correctly, with respect to using this assumption from the beginning and doing the analysis in the classic way. But at the same time, it will provide you a different mindset on how to analyze optimization algorithms, because the fact that you know that the environment is adversarial will give you this advantage of saying in each time step, what's the worst thing that can happen? What's the worst loss that I can receive? What's the worst gradient that I can get? And that will tell you basically what is the right thing that the algorithm should do in order to be robust to anything. However, there is this other thing that I believe is more important, that online learning, it's connected to a number of other topics. So it's connected to generalization, pack-based, compression, betting, and I will try to show you some of these connections. Now, there are some algorithms that you might already know, and maybe you never realized that they actually come from online learning. Of course, online gradient descent, this comes directly from online learning, but for example, AdaGrad, that for a period was massively used in deep learning, it's an online learning algorithm. If you look at the paper, there is a regret guarantee. There is nothing about stochastic optimization. There is nothing about deep learning, by the way, in the entire paper. And more recently, AMS-GRAD, that was basically an algorithm that was designed to fix an error in the proof of Adam. Again, it's an online learning algorithm. If you look at the paper, you will see that they basically prove a regret guarantee. And so all these algorithms were designed to work in the adversarial setting. And for all of them, what people show, it's basically that the regret is square root of t, where capital T is the number of iterations, so that again, the average regret will go to 0 over time. But as we'll see in a few slides, they can also be used as stochastic optimization algorithm, and the convergence rate is basically 1 over square root of capital T for all of them. Okay, so in the following, I will use few assumptions and definitions, and they will be always the same throughout all these 3 hours. We say that the algorithm is receiving a sequence of losses. The losses are from RD to R. We will assume that there are always convex, and we will always assume that there are one Lipschitz with respect to the norm that is the relevant one. It depends on each single framework. The feasible set V, it's always a convex, closed, non-empty subset of R to the D. And there are a number of technical conditions that we should make in order to be sure that the iterate of the algorithms do exist in each round. I will not mention them. Be sure that they are true, the iterate do exist. Okay, so there are many, as I told you, there are basically mainly 2 meta algorithms that cover 90% of online optimization. And by the way, not only online optimization, this is also true for classic optimization. These two algorithms are basically online mirror descent and follow the regularized leader. And so, for example, online gradient descent is a special case of online mirror descent. Dual averaging, it's a special case of follow the regularized leader with linearized losses. I don't know, something a little bit more complex. Accelerated algorithm is just two online convex optimization algorithms that are playing against each other. Same thing for Frank-Wolf, and so on. And so, once you study these two families of algorithms, you can basically, through reductions and through basically minor variations, you can cover basically 90% of what is optimization. And so let's start with the first one, and let's start with a simpler version of online mirror descent, that is online subgradient descent. So online subgradient descent, let's start with something even simpler, that is online gradient descent, projected. And you might already know this one, because this is basically the algorithm that people use in machine learning 90% of the time. So what you have is a feasible set. You need an initial point in your feasible set, and you need a bunch of learning rate. And basically, in each round, you output an x of t, you pay the value of the loss in x of t, and then you receive the value of the gradient of the loss in the point that you generated, gt. And the update is very simple. The update, the xt plus 1, is equal to the projection onto the feasible set of xt minus learning rate multiplied by the gradient. Now, as I told you, I want to show you proofs. So we'll show the regret of this algorithm. And it's very, very simple. So the first thing that we do is that we want to show what is the progress of the algorithm in each step. And so we will have this simple lemma that says that the loss of the algorithm evaluated in the point that he predicted minus the loss of any vector view is less than the difference between x of t minus u in two different steps, plus the gradient squared. And the learning rate is appearing here at the beginning and here with a square term. Okay, so how do we prove it? It is extremely simple. We just look at the difference between of the L2 norm squared between the points generated by the algorithm and the competitor in two different time steps. Now, the first thing that we observe is that given the update of the algorithm, xt plus 1 is the projection of xt minus eta t gt onto the feasible set. Now, the projection is non-expansive, so this distance, the moment that I do the projection, will just decrease. So if I remove the projection operator, I get something that for sure it's bigger or equal than xt minus u. At this point, I just expand this square term here, and I consider xt minus u as one term, and the gradient multiplied by the learning rate as the other term. And xt minus u squared will simplify this other term, so what I get is just the cross product and the gradient squared multiplied by the learning rate squared. Now, at this point, I remember that gt is the gradient, and these are convex functions. And so I can immediately say that this term here is lower bounded by minus the difference between the loss in xt and the loss in u for any u. And that's it, the proof is finished. So I just have to reorder the terms and I obtain this statement that I showed you. Now, from this small lemma, proving the regret guarantee, it's again really, really simple. Now, I want to show that the sum of the losses suffered by the algorithm minus the sum of the losses suffered by any vector u is less than, and here I want to introduce you this RGB notation. So this term is the initial condition, will be always be in red in these slides. This term is related to the gradients and it will be always be in green. And this term is negative and will always be in blue. So this term, the term that is in blue, it's negative. I will basically remove it all the time. It's important to remember that it is there because this is the term that you use if you want to show that the iterates of your algorithm are bounded. But we will not do that. And so the only two terms that we have to remember is in red is the initial condition and in green is the term related to the gradients. So how do we show this inequality? We basically take the lemma that we showed before, and we just sum it over time. So we had the lemma was just what happens in a single round. We just sum that inequality that was basically this one for a single t over all the rounds. Now, what happens is that if you observe this difference here, this is what we call the telescopic sum. Because for t equal to 1, here you have x1, and here you have x2. In the second term, here you have x2, and here you have x3. So x2 is appearing first with a plus sign, and then with a minus sign. And so they basically simplify each other when you do this sum. And so the only terms that will survive in this sum are the first one and the last one. This is what we get, the first one and the last one, and then the sum of the gradients is just the sum of the gradient. That's it. This is the regret guarantee. Okay, so now let's try to go immediately beyond this algorithm. This is very, very simple, but it's not enough. It's not enough because we assume that the functions are convex, but they have to be differentiables because we have to calculate a gradient. Now, a lot of functions are convex, but they are not differentiables, like very simple ones, like absolute value or the ReLU functions. And so we want to go beyond the notion of differentiability. However, we have to remember that the only place in the proof in which I used the fact that the functions was differentiable was to use this simple inequality. This simple inequality was the only place in which I used the fact that I use gradients and convexity, nowhere else. And what is this inequality? This inequality says, every time I have a gradient, I can construct a linear lower bound to the functions if the function is convex. So if you give me any other vector that satisfies this inequality, that is not a gradient, but satisfies this inequality, the entire proof will go through. And this is exactly what we do. So now, instead of using the gradient here, I use any vector gt such that this inequality is still true. It turns out that this notion, it's a known notion, it's called subgradient. And the subgradients of a convex function, it's a very strong, it's a very good concept to use because the subgradients of a convex function, they basically always exist. It doesn't matter if the function is differentiable or not, the subgradients always exist, up to technical conditions. The weird thing of subgradients is that there might be an infinite number of them. So for example, if you consider this function here, this function is convex, it's not differentiable here, but remember that the subgradient, the only thing that it has to give me is the possibility to construct a linear lower bound. So if you look here, this line is a linear lower bound to this function, and is constructed to a subgradient that is a number, because this is a one-dimensional function, a certain number. However, there is also another possibility. I can also draw a line that's like this, or I can draw an horizontal line. So it turns out that in this point here, the number of subgradients is actually infinite. And for the algorithm that I showed you, and for the proof that I showed you, it doesn't matter which one you pick. The entire proof will go through. It doesn't matter which subgradient you pick. Now, given that the subgradients can be infinite, we will call the subdifferential set, the set of all the subgradients in a certain point. And we will denote it with this symbol here, partial LT of xt. And so, for example, here, to be more specific, the set of subgradients in this point, this is the function absolute value of x minus 1. So in 1, the set of subgradients is all the number between -1 and 1, including the extremes. Okay, so immediately now we can, as I said, we can go from gradient to subgradient, and so we get projected online subgradient descent. The only line that you have to change in your algorithm is the fact that GT now, instead of being a gradient, it's a subgradient. Which subgradient? It doesn't matter. Just pick up one of them. And I want to stress that this is particularly important that works for any subgradient, because most of the time you are not the one choosing the subgradients. Somebody else was choosing it for you. Let's consider a very practical example. Use PyTorch, and you ask PyTorch for the subgradient of the ReLU. PyTorch will give you one subgradient in 0. You are not the one choosing it. It's the developer of PyTorch that were choosing it for you. And the guarantee is exactly the same because, as I told you, the only place in which we use the property of the subgradient was to prove that inequality. That inequality is true by definition with the subgradient, and so the regret is exactly the same. Okay, so now that we have this regret, I told you that we would like the regret to be sublinear in time. It's not immediately clear that this is sublinear. In fact, this is not sublinear because this is the sum of t gradients. And the gradients can be different than zero. The subgradient, sorry, can be different than zero. And so this sum seems to be of the order of capital T. Now, let's assume, as I told you a few slides ago, that everything is Lipschitz, all the functions are Lipschitz, and they're all Lipschitz 1. So this means that each one, if the functions are Lipschitz, the subgradients in norm are bounded by the Lipschitz constant. So this means that each one of these is bounded by 1, and I have capital T of them. And so my regret becomes initial condition plus T times learning rate divided by 2. Okay, now from these, now I have to choose the learning rate. And this is easy to do because this is basically a convex one-dimensional function in the learning rate. And so I can immediately choose what is the optimal learning rate. And so I just solve this one-dimensional convex problem and I obtain the optimal learning rate. And so the optimal learning rate says you should use a learning rate that is proportional between the competitor U and the initial point divided by the square root of the number of iterations. Now, if you do that, I'm sorry I didn't write it on the slide, you will get that the regret will become U minus x1 square root of t. And so you get that the regret is square root of t, so that on average will go to 0. However, do you see any problem with this choice? The problem is the following. The problem is that U is not a fixed vector. U is any vector. So this definition doesn't make any sense because, this is not a fixed vector. The other problem is that suppose that you choose a U and you say, I want to compete with a particular U. And so I choose a particular learning rate and I plug into my algorithm. I told you the adversary is selecting the losses in order to screw you, basically. And so the adversary knows what you're doing. The adversary knows what is the learning rate that you're using. So the moment that you select a particular U, it will change all the losses so that the U that you selected, it's useless. Okay. So this choice, first, it's ill-defined, but it's also useless because the adversarial nature of the game will make this choice useless. And so what people do in practice, and what people do in practice even when they use it for this algorithm, for example, in machine learning, they basically say, okay, I have no idea what to put here. Let's put alpha. Alpha divided by square root of number of iterations. Now, what happens is that this is not the optimal learning rate anymore. And so basically you pay now this term here in which you couldn't solve exactly this trade-off between this term and the constant term. The regret will still be square root of t, but now this quantity here will basically depend on x1 minus u with a square. Again, if you're able to do this optimally, you would remove the square, but given that you're not able to do it, you will just pay this quantity with the square, and depending on alpha. And by the way, what is the alpha that people use? Well, if you do online learning, typically alpha is 1. If you are a deep learning person, the alpha is typically 0.0001, for no reason, by the way. Now, there is an easy case in which you can actually solve this problem. You can say, in the case in which the feasible set has a bounded diameter, in this case, you can say, well, I still don't know what is U, but I know that regardless of the choice of U, given that I am in a bounded domain with a bounded diameter, U minus x1, if the bounded diameter is d, is bounded by d. And so now this is d squared divided by eta plus number of iteration multiplied by learning rate. I can solve the trade-off exactly. And so the learning rate is diameter divided by square root of t. That gives me the regret that is d square root of t. And this is optimal in this particular case in which the diameter is bounded. And this is what you will find, by the way, 90% of the online learning papers. They will say your feasible set is bounded, even if it's actually not true. Most of the time, it's not true. Okay, so given that now we did our first algorithm, it's a good moment to show you how to go from online convex optimization to standard batch and stochastic optimization. The reduction is extremely simple. The reduction says you have a stochastic or an optimization problem, and you have an online learning algorithm. You have to construct an online learning game out of your optimization problem so that you can use your online convex optimization algorithm. So in each round, you get XT from your online convex optimization algorithm. And let's say that you're in the stochastic setting. So you receive a subgradient GT such that the conditional expectation of GT belongs to the subdifferential set of the function that you're trying to minimize in X of t. Now, with this GT, you construct a loss. You construct a linear loss. And the linear loss is just inner product of GT with X. And you pass this loss to the online learning algorithm. The online learning algorithm will minimize the regret of any loss. Remember that we don't make any assumption on how the losses are generated, right? So the environment can generate losses, but you can also generate losses and pass to the online learning algorithm. It's completely fine. And so this is the loss that you generate. You pass to the online learning algorithm. The online learning algorithm will update, and in the next round, it will give you another X of t. Now, at the end of this entire procedure, you take the average of all your iteration, and this is your final solution. So what we can show is that the expected value of the function that you're trying to minimize in the average of the iteration minus f in any u, and again, I want to use the fact that this does not have to be the minimizer of f, because again, the minimizer of f might not exist, is less than the expected value of the regret in u divided by capital T. Okay, so the theorem basically says every time you have a regret guarantee, if you divide by capital T, you get a convergence guarantee. Okay, this is what you should think in your mind. Everything that you see regret is square root of t. This corresponds to 1 over square root of t convergence rate for the suboptimality gap. Okay, the proof of this is also extremely simple. So you start from this quantity. This is the quantity that you want to upper bound. Use Jensen inequality, because this was the average of all the iterates. And so the functions are convex. And so this is the less than the average of the difference between f of x of t and f of u. Now, you use the fact that the functions is convex and the fact that the conditional expectation of GT is a subgradient. And so by definition of subgradient, you can upper bound this difference between function value with the inner product between this subgradient and xt minus u. Now use the fact that this is conditional expectation. So condition on the past, xt and u are fixed. So you can put the conditional expectation over the entire expression. And you use the law of total expectation to remember that this expression here is nothing else than the expectation with respect to all the randomness. And that's it, it's finished, because this expression here, the sum of this expression, if you put the expectation outside, it's nothing else than your regret with respect to the linear losses that you pass to the algorithm. So this is equal to the expectation of the regret in U divided by capital T. Okay. And so from these, you can immediately get stochastic subgradient descent. That it's what basically 90% of the people use in machine learning. That basically says in each round you output an x of t, you receive a stochastic gradient or subgradient gt, and in each round you do the update xt minus learning rate gt, and if there is a feasible set, you project onto the set. If there is no feasible set, the projection is not needed, and theoretically at the end you should also take the average of your iteration. The regret guarantee that we get is that if you choose the learning rate as alpha over square root of t, you just have to take the regret guarantee that I showed you before, divided by capital T, and that's it. You get your convergence rate guarantee. The only thing that you have to assume for the entire thing to go through is that f has to be convex. Okay, so now let's go. Yes.
In what sense is G stochastic, the gradient?
G can be generated in any way you like. The only thing that you need is that the conditional expectation of GT is the right thing that you're trying to calculate. Okay, let me give a practical example. You have a training set, and you should calculate the gradient of your objective function over the entire training set. How do you do that? You average the gradient over the entire training set. This is the true gradient. Now, what is a stochastic version of this? You take a mini batch over a random subset of your training data. This thing in conditional expectation will be exactly the true gradient. This is one example. Another example, instead of taking a mini batch, take just one sample at random. It's still good. Any way you like, you know. Okay, so now let's try to go beyond online subgradient descent. And the way to do that is first I want to remove some of your intuitions that you might have about subgradients. So how does subgradient descent work? Now, in your mind, you might think subgradient descent works because this subgradient is telling me where to go. It's telling me the direction where there is the minimum. Well, this is wrong. This is wrong even for gradients. For gradients, this is already wrong, and please, you should already not have this intuition in your mind. But for subgradients, it's even more wrong. And why that? I hope you can see the figures. Yeah, it's good. So let me show you an example of this. This is a convex function, and this is the formula. This is a two-dimensional convex function. So this is x1, x2, and this is the value of the function. And it's created as a max of 3 linear functions. Now, linears are convex, max of convex is convex, so this is a convex function. And these are the contour lines, the sub-level sets of the function. So each line here is connecting all the points in which the value of the function is the same. So if I move along a line, the value of the function is always the same. The minimizer is here. Okay. Now I put myself here on this corner. On that corner, the function is not differentiable. I have to receive a subgradient. Remember, you don't choose the subgradient, somebody chooses for you. The negative subgradient that you got is this one. This is a legal subgradient. The problem with it is that when you move along this direction, the function does not go down. The function is constant up to this point. And then what happens at this point? The function goes up. So it doesn't matter which learning rate you use. It doesn't matter how much you jump in that direction. The only thing that can happen is the function stays constant or it goes up, okay? But it gets even worse. Let me show you another example. This is a max of 2 quadratic functions. And again, the minimizer here, it's here in the middle. You are here in one of these corners. You get one of, this is the negative subgradients that you got. Here, in this direction, the function goes only up. It's the only place where you can go is to increase the function. So you can see that it's not pointing towards the minimum. It's not even pointing in a descent direction. It's pointing in a direction in which the function is increasing. Now, what you could do in this situation, you could say, oh, wait a moment, the function is going up. I cannot go in that direction. I don't move. Well, this is a bad idea because let's say that this is batch optimization. Now, in the next iteration, you are in the same point. You receive the same subgradient. What do? You're still there. You have to do something. You have to move. You have to go up. So when you use subgradient descent, you will go up. It's unavoidable. It's not because you choose the learning rate in the wrong way. It's just because subgradients are a very, very weak notion of where you should go. Okay, so you have to accept the fact that subgradients are weak. They are not pointing towards the minimum. They are not a descent direction in any way. Okay, so if subgradient descent is not working because I am going towards the minimum, why they are working? There is actually another reason. And this is what we have to understand in order to extend online subgradient descent. So let's start from the update. We say that we do xt minus learning rate multiplied by our subgradient, and then we project. So we can rewrite it. Remember that Euclidean projection is written as the argmin of x minus your update. Now, the square doesn't matter. I mean, I can put the square, I can remove the square because this is an argmin. So the position of the minimum does not change if I square my function. And now what we do is that we just expand our quadratic form. So we have the square of one, the square of the other, and the cross product. Now, observe the fact that, again, this is an argmin, and this term is constant with respect to x, that is the variable with which I am minimizing. So I can remove it, I can add it, the minimum will change, but the argmin will not change. So I want to remove this term, And also another term here is the inner product between gt and xt. Again, this is a constant term, but I want to remove some terms and add some other constant terms so that nothing changes. And so I want actually to consider this expression, okay? And now that I look at it, there is an error because it should be minus x of t, okay? So what is this expression here? This is the linear approximation to your loss function in x of t. And given the property of the subgradient, this is always below the function, okay? And what is this other term here? This other term basically says, this is minimized when x is equal to x of t. So basically what you are doing when you calculate your update for online subgradient descent is that you are basically minimizing two terms that are one against the other. One term says, I would like to minimize a linear approximation to my function. And by the way, if the set here is the entire RT, this is a linear function. So the minimizer is at infinity. So this is not a very good objective on its own. But the other one says, by the way, you should not go too far from x of t. And what is regulating this trade-off between these two terms? The learning rate. The learning rate basically says how important is one term against the other. Okay, so this is the actual reason why online subgradient descent works. And this is what you should remember. You are basically minimizing an approximation to your function, constrained to the fact that you don't want to go too far from where you are. And this should be intuitive, by the way. It's an approximation to the function. It's a linear approximation. I mean, this is basically a Taylor expansion, if you want, truncated to your first term. Forget about the fact that the function is not differentiable. It's not really important. It's a Taylor approximation. So the Taylor approximation is good around the point, but if you go far from the point, the Taylor approximation will be terrible, right? And so this other term says, do not go too far. And so this is a picture of what's going on, basically. This is the black line is your convex function. You are here. The blue line is your linear approximation to the function, that given that the function is convex, it's always a lower bound to the function. And the red line is the sum of the linear approximation plus the quadratic term. And you will see, you can see that the minimum is somewhere, not exactly in x0, but not at infinity, somewhere close to x0. And how far it is, it depends on the learning rate that regulates how important are these two terms. Okay, so now that we have this intuition, now that we understand a little bit better why online subgradient descent works, you should be able to see that there is actually no reason to measure the distance between x of t and x with the Euclidean norm. Because this term is basically saying you should be close to x of t. But why I should measure distances with the Euclidean norm? I mean, Euclidean norm, it's a very specific way to measure distances. So it turns out that I can generalize this term here using what they are called Bregman divergences. Now, one might think of, instead of the Euclidean norm squared, I want to use another norm squared, but it doesn't really work. The right thing to use is actually Bregman divergences. So what is a Bregman divergence? Let's take a function psi that is strictly convex and differentiable in the interior of its domain. The Bregman divergence with respect to psi, and psi is called distance generating function, is defined as psi of x minus psi of y minus the inner product between the gradient of psi in y and x minus y. Now, I have zero intuition on this Bregman divergence, and I think it's actually useless to try to gain one. But let me try to tell you what this thing is. This is basically the function psi in x minus the first order Taylor approximation of the function centered in y. Okay, this is basically the definition. And so the Bregman is in x around y. This is how you should read it. Okay, so what we can do now with this thing, we start from our online subgradient descent update, and we'd say, okay, instead of using the Euclidean norm squared, let me actually use this Bregman divergence. And now you see that this Bregman divergence depends on psi. So this is not a single algorithm anymore. This is a family of algorithms. For every psi, I will get a different algorithm. And so this is the algorithm. And this is what we call online mirror descent. And so everything is the same. The only thing that changes is that now I have the Bregman here instead of the squared Euclidean norm. Now, in order to show you the bound, we have to define what is a strongly convex function. Now, a function from Rd to minus infinity plus infinity is lambda strongly convex with respect to an arbitrary norm if, focus for a moment just on these terms in black. These terms in black basically are what any convex function would satisfy, because G is a subgradient of f in x. So by the definition of subgradient, this is true for any convex function. And this again says you can construct a linear lower bound. But strong convexity tells you something stronger. It gives you this additional quadratic term that depends on the norm here and depends on lambda. And this term basically says you can always construct a linear lower bound, but you can construct something stronger. You can construct a quadratic lower bound to your function. So this is the intuition that you should have. Strong convexity allows you to construct quadratic lower bounds. So basically it tells you what is the minimum curvature of the function because it's a quadratic. You cannot construct a quadratic lower bound on a linear function, right? And so a linear function will not have strong convexity. But if you have something that has a little bit of curvature, the strong convexity is the minimum curvature that you have. Now, with strong convexity, you can immediately get these two lemmas. And the one that we will use is this one that basically says, if the function psi is lambda strongly convex, then immediately the Bregman divergence is lower bounded by a quadratic. And so basically you can think of that the fact that the Bregman divergence is behaving like a norm squared. A difference between two vectors is norm squared. Okay, I will skip this proof, but I will just show you the regret. And the regret of online mirror descent, now the only thing that we have assumed is that our distance generating function is lambda strongly convex with respect to a norm. In the regret again, we'll have these three terms. Remember the colors. There is the initial condition, there is the term related to the gradient, and there is a term that is negative. So the initial condition now it's the same as before, but now we use Bregmans to measure distances between u and x1. The term related to the gradients, there are two differences. It got divided by the strong convexity. And now there is the norm that is appearing here. It's the dual norm of this guy. So the strong convexity is with respect to a norm, and the gradients are measured with respect to the dual norm. Again, I will not go over the proof, but be sure that if you want to go it offline, the proof is correct. And this is the entire proof. Okay, let me show you an example. So on line subgradient descent, so the same algorithm as before, if we say this is a generalization of a line subgradient descent, we should be able to recover it immediately. And so how we do that, we choose psi equal to 1/2 norm of x squared, where the norm that we choose is the L2. Now it's easy to show that this is one strongly convex with respect to the L2 norm. And what is the dual norm of the L2 norm? It's the L2 norm. And the other thing that we need to calculate the Bregman divergence. So the Bregman divergence is psi of the first minus psi of the second minus gradient of psi in the second and first minus second. This is exactly equal to 1/2 x minus y L2 norm squared. And so if you put everything together, this is the bound of online mirror descent, where I removed the blue term because it's negative. And so now we have just this term is the Bregman. This is our Bregman, so we just substitute it. And the dual norm here is just the L2 norm. And the strong convexity, it's 1. And so we get a 1, and we go back to the bound that I showed you before. Okay, so it does work. But let me show you something a little bit more interesting, a little bit more exotic. Let me choose a very different distance generating function. Now, the feasible set, it's a very special one because it's the set of discrete distributions. So I have the set of all the vectors in RT such that the coordinates are positive and the L1 norm is equal to 1. So basically these are discrete distributions. Okay, so I'm doing optimizations over distributions. And the psi is the negative entropy of these vectors. Now, it's possible to show that this psi is one strongly convex with respect to the L1 norm. And the dual norm of the L1 norm is the L infinity norm. And so now I have all the ingredients for my regret, but I also would like to know what is the actual algorithm. If I actually solve that argmin with this particular choice of the Bregman divergence, I get this very weird update. So let's take a moment at what this update is doing. Let's ignore for the moment the normalization factor here. So the update goes over each single coordinate of your vector. And so xt plus 1 at coordinate j is equal to xt at coordinate j. Here, normally what you would do in all the gradient descent algorithm, it's basically you add the gradient, right? With a learning rate and a negative sign. Here instead, you are multiplying the coordinate j of your vector by the exponent of minus learning rate and the coordinate j of your gradient, okay? And now, and you do this for all the coordinates, and then you divide it by the sum so that you get a probability distribution again, okay? Because you are doing optimization over probability distributions. Each vector has to be a probability distribution. So these are all positive numbers. If you divide it by their sum, you get a vector that has L1 norm equal to 1. So you get the probability distribution, okay? This thing is called exponentiated gradient. Or it's also called hedge, or it's also called exponentiated weighted algorithm. It has a million names, but at the end of the day, it's all online mirror descent with the entropy as distance generating function. Now, why this is an interesting algorithm? Let's look at what we get if we plug our regret guarantee. So we need the Bregman and we need the dual norm. We know that the dual norm is the infinity norm. Let me assume that, again, as I told you at the beginning, everything is Lipschitz with respect to the appropriate norm. So these gradients are 1. The interesting thing here, it's here. What is this Bregman term? The Bregman term with respect to the entropy is the KL divergence. That, by the way, it's called divergence because it is one of the divergences that can be expressed as a Bregman. And so you get the KL divergence between u and x1. And this term can be upper bounded by the logarithm of d when x1 is the uniform distribution. Okay. And now if you do, you get log t over learning rate, and learning rate, number of steps divided by 2. If you tune the learning rate optimally, you will get an algorithm whose dependency on dimension is just logarithmic. And so this is a very interesting algorithm, and this is basically the basis if you do learning with expert, if you do bandits, all these algorithms are based on this algorithm. Okay, now this was online mirror descent. Let me now move to the second class of algorithms that is called follow the regularized leader. Now, if you understood what we did till now, online mirror descent has a key idea. The key idea is that I want to minimize a linearization of my function, but I don't want to go too far from the current point. What is the intuition instead of beyond follow the regularized leader? It's not really different, but it has some differences. Here, instead of saying I just want to minimize the last loss, here we say I want to minimize all the losses that I received till now, but I don't want to go too far from a fixed point. Okay, so this term here basically that can change over time, but basically says I don't want to go too far from a fixed point, and here I just minimize all of them instead of minimizing just the last one. And that's it. This is the entire algorithm. This is called follow the regularized leader. Now, what we can show for this algorithm? For this algorithm, we can show a regret that again is composed by 3 parts: the red part, the green part, and the blue part. The red part is still the same thing, initial condition. They basically measure how far you are from the competitor u and your initial point. Sorry. The green part will be again a term that depends on gradients, and I will show you why it depends on gradients in a moment. The blue part is again something that is negative, so we discard. Now, the nice thing about this algorithm is that this thing is inequality. So I will not show you the proof because there is nothing going on here. I mean, you just have to bang on it hard enough until you get 0 equal to 0. You just have to remember this thing here. And by the way, this holds for, I don't have to assume anything for this equality to be true. This is true for any set of functions, even non-convex, even a non-convex set. This entire thing is true without assumptions, basically. Now, that 3 terms there in green, if the sum of the functions that I observed plus my regularizer are strongly convex, it can be upper bounded by the gradient, the subgradient squared in dual norm divided by 2 times the strong convexity, plus a term that depends on how your regularizer is changing over time. This psi, we call it regularizer. And this is the psi evaluated in the same 2 different psi evaluated in 2 different points. I will skip over this proof because it goes through some annoying convex analysis details. But the thing to remember is that these green terms becomes basically gradients. And so we look at these 3 terms. Here, the blue term is negative. These green terms can be upper bounded by these. And so we get our FTRL guarantee. And this is basically the same thing as before. This is the same bound that we got for online mirror descent. There is an initial condition, and there is a sum of gradients divided by the strong convexity. But the difference is that the strong convexity before was fixed. Now the strong convexity now is changing over time because it depends on your regularizer that is changing over time. Okay, let me show you an example, what we can do with this followed regularized leader. Let's play a game. The game is the following. You have to create in your mind a number between 0 and 1, okay? And I have to guess it. This is an online learning game. You are my adversary. So you are allowed to cheat in the sense that you are the adversary. You can decide to change your number after you see my prediction, okay? So, because again, you can create your loss after you see what I have done. So I say, I think that you are thinking of 0.3, and you say, sorry, I was thinking of 1. And we keep doing this for all the rounds, okay? So this is an online learning game, so we want to minimize the regret. So we want to minimize the difference between the losses that I pay and the losses of a fixed prediction. So saying all the time a fixed number in each round. So I have to define losses. The losses that I want to use is the difference between the number that I guess and the number that was the true number that you told me, squared. Okay, it's just square loss. Okay, so what we use here, we use FTRL, we use follow the regularized leader, but even without regularizer. So this is actually called follow the leader because there is no regularization. And again, follow the regularized leader says you should just minimize the sum of all the losses till now plus regularizer. There is no regularizer. So this basically says in each round, what I do is that I minimize the sum of all the losses in the past. So the losses are just the squared loss between x and the points that you told me you were thinking. So this means that in each round, I can just calculate exactly this argument. In each round, I have to predict with the average of the numbers that you told me till now. That's it. Okay. Now, it would seem that this is sort of a stochastic approach. It would seem that you're thinking, oh, the adversary is a stochastic distribution, and so I'm basically trying to estimate the mean. But no, this entire thing works regardless of how the adversary is generating the numbers. So what do we get? We get that the sum of these things is 2t strongly convex because each one of them is strongly convex. Each one of these things is strongly convex because it is lower bounded by a quadratic because it is a quadratic. So each one of them is quadratic, and the strong convexity is 2. I have t of them, and so the strong convexity of each one of them is 2t. And the gradient, this is my gradient, and given that the numbers are between 0 and 1, the gradients in absolute value is bounded by 2. And so my regret is upper bounded by the gradient squared divided by the strong convexity. And so I have the sum of 2 divided by t, and the sum of 1 over t can be always upper bounded by log t. And so that's it. This is the regret. The regret of this algorithm will be logarithmic in time. And I want to stress that, again, I'm not assuming anything on how you generate your number. It doesn't matter how you do it. You might do it after I predict in each round my number. This cumulative sum between what I do and the cumulative sum between a fixed, predicting any fixed number in each round, on average goes to 0, and goes to 0 pretty fast, by the way, because log t, it's basically almost the best thing that we can achieve in online learning. The best thing would be constant regret. This is a little bit, worse than constant, but not too much. Okay, now follow the regularized leader, it's kind of a weird algorithm because it's very powerful, but in each round, I told you, you have to minimize the sum of all the losses that you saw till now. This is a convex optimization problem. And this is a convex optimization problem that becomes harder and harder over time because you are adding stuff to your sum. And the losses that you receive are arbitrary. So you receive arbitrary convex losses, you sum them together, in each round you have to find the minimizer. You really don't want to do that. I mean, you could do that, but you really don't want to do that. And so remember, this is online learning. We can construct the losses ourselves. The algorithm will still work. The regret will still work. And so what we do is that instead of using the real losses, we still use FTRL, but over a sequence of surrogate losses that we construct. Okay? And what are the surrogate losses that we construct? We use the linear approximation. Okay, again, here there is a -xt term missing. So this is, again, something like a Taylor approximation to the first terms of all the losses that you observe. Okay, so instead of minimizing the sum of arbitrary complex convex losses, you now minimize a sum of linear functions. And this is a much, much easier problem than before. And so now the algorithm becomes this, FTRL with linearized losses. In each round, you minimize the sum of a regularizer plus sum of linear terms. And how these linear terms are constructed, each GI is the subgradient of the loss in the point that you predict. Okay? And this is way easier than before because this is now just a convex function. And by the way, you are choosing the regularizer. So if you're smart enough, you will choose a regularizer that is nice and easy to be optimized. And this is just a convex term. And so most of the time, now with this version, you can have a closed formula. XT will have a very nice closed formula, and you don't have to solve a full-fledged optimization problem in each round. How much you pay for it? Nothing. You don't pay basically anything in the case that the losses are Lipschitz. You don't pay anything in your regret. Why you don't pay anything? Because you would like to minimize this regret with respect to the actual losses, right? But remember that this difference here, it's always upper bounded, each one of them, it's always upper bounded by these linear terms, by the definition of subgradients. This is exactly true because GT are subgradients. So this inequality, it's always true. Now, what is this thing? This is the regret with respect to the linear losses, where the linear losses is GT XT. So this is the loss of the algorithm, and GT inner product U is the loss of the competitor. So this is the regret of the linear losses, and this is exactly the losses that you're using in FTRL. And so given that these are the losses that you're minimizing, the regret on top of this quantity will be square root of T, and this implies also square root of T on the original losses. Okay, and so you didn't lose anything. The entire thing still works, but now you have a very, very, very simple algorithm to run. As simple as online mirror descent. Now, I want to show you a very critical difference between online mirror descent and follow the reader with regularized losses. In some cases, in most of the cases, these two algorithms will be very, very similar, but they have a very specific difference, and I want to stress this difference. Let me consider that the feasible set is the entire space. Okay, so there is basically no feasible set, it's unconstrained. And let me use in FTRL, the regularizer is 1 over something, let's call it eta t. I don't want to call it learning rate, but just let's call it eta t. Norm of x squared, and the norm is L2. Now, this thing is 1 over eta t strongly convex with respect to the L2 norm, because again, this is a quadratic, and the coefficient of the quadratic is the strong convexity. Now, we said FTRL is just the regularizer, and these are the linearized losses. There is no feasible set. So this argmin, it can be solved immediately. Well, it should be easy. It's a convex function. I just have to calculate the gradient, put equal to 0. I get my update. Okay, so this is the update of FTRL. Now, let me compare to what online subgradient descent would do. Online subgradient descent, let's say that we start from 0, and again, there is no projection because there is no feasible set. So in each round, we do xt minus learning rate gt. Let me unroll this thing till the beginning, right? Where the beginning was 0, we get minus sum of the subgradient, each one of them multiplied by learning rate. So look at these two algorithms. They're very, very, very similar. If the learning rate is constant, they're actually the same. They would be exactly the same algorithm. But if the learning rate is not constant, these two algorithms behave differently. And in particular, in online subgradient descent, if typically use a learning rate that is decreasing over time, you introduce new information in your solution with a decreasing weight. Okay, because each time you add something with a smaller and smaller weight, that is your learning rate. Instead, in FTRL with linear losses, the gradients are entering in your solution with a constant weight. All of them are equally important, but then you rescale them, all of them equally with the same learning rate. Okay? And this was, by the way, exactly the intuition. FTRL with linearized losses is also known in the optimization community as dual averaging. And dual averaging was proposed by Nesterov, Nemirovsky, one of the two. And if you read the original paper, you will see that this is exactly the motivation with which this algorithm was introduced. Basically, the paper says, I'm doing an optimization algorithm, and my intuition says, I'm going closer to the solution, closer and closer, so my gradients are better and more informative, and I'm putting them in my solution with a decreasing weight. And this seems counterintuitive. And this was dual averaging instead is introducing them in your solution, all of them with equal weight. Okay, and this seemed to the author like the right thing to do. At the end of the day, the convergence rate is the same, but it might be good to remember that there is this critical difference between these two. The other thing that I want to notice is that in online subgradient descent, what you do is that you really take a jump each time by the subgradient multiplied by the learning rate. And so, by the way, in machine learning, people call it learning rate, but in optimization, they call it step size. That is a much better word for it, because you basically say, what is the size of your step each time? In follow the regularized leader or dual averaging, you're not doing that. This is not really what's happening. This thing is not a step size, because every time you take the entire sum and you rescale the entire sum. So this is not really a jump of size eta t. Now, these two differences are important to remember, but also I think it's also one of the reason why nobody understands FTRL. There is basically no one that is using FTRL or dual averaging, and especially optimization people, they seem not to understand what's going on. But it's at the end, it's very, very simple, and everything goes back to these few key differences. Let me show you an example. FTRL, linearized losses, Euclidean regularization. So let's say that, again, there is no constraint. My regularizer, it's always the same, it's constant, and is some gamma divided by 2, norm of x squared L2. This is gamma strongly convex, because again, this is a quadratic. The dual of the L2 norm is the L2 norm. And so the update will be the sum of the gradients divided by gamma with a negative sign. And the regret becomes, this is the generic regret of FTRL. Now, the strong convexity is just gamma. The dual norm is just the L2 norm. And this thing, if you just calculate it, it's very simple, because the minimum of the regularizer are all the same. They don't change over time. The minimum of the regularizer is 0. And so this term is 0. And this is just the regularizer evaluated in U. Okay. And so you get basically the same regret bound of online subgradient descent and slightly different update. Now, here, sorry, this should be gamma. What is the optimal tuning of gamma? And I want to ask you this question because I want to show you that FTRL didn't really solve the problem of tuning gamma. The problem is still there. If you would like to tune gamma, you have the same problem as before. You should know U. What is U? U is not even a fixed vector. And even assuming that there is a fixed vector, like, there is a minimizer of all the losses, you can consider that as your U. I want to compete with the minimizer of all the losses. You don't know the norm of X star because that accounts basically to know the future. And even in stochastic or batch optimization, you don't know the norm of the optimal solution because you're looking for it. You're running an optimization algorithm. If you knew what was the optimal solution, there was no need to run the optimization algorithm in the first place. And so this problem was in online subgradient descent, in online mirror descent, and the same problem is in FTRL. Okay, so that problem is still there. So now let me move to a class of algorithms in which this problem is not there. We found a way to remove the fact that you should know the future or something about you. So we define this class of algorithms we call them parameter free. So what do we mean by that? In a very, not very precise way, let's define a parameter free online convex optimization algorithm as one that achieves the optimal regret uniformly for any competitor U up to logarithmic factors. Okay? So for any competitor U, you should get the best possible regret, as if you tuned your learning rate with the knowledge of U. Okay? So for example, if I show you exponentiated gradient, the algorithm that I showed you before, there was this KL divergence, and I told you, oh, the KL divergence can be upper bounded by logarithm. But let's say that I don't want to upper bound it. I just want to keep the KL divergence like this. If I do the trade-off correctly, I should get square root of T KL divergence. And this is possible. This is completely possible. This algorithm is called normal edge. And this algorithm is strictly better than edge or EWA or any other algorithm that people use for learning it with expert. This is always better because there is nothing to tune and achieves the optimal regret as if you tuned the learning rate with knowledge of the future. What is the price that you pay? The price that you pay is this +1 here, that it's probably fine. There is an equivalent problem in online subgradient descent. We saw that you had to tune the learning rate, you had to know x1 minus u. This is impossible to know. And so it's impossible to tune the learning rate, but there is a class of algorithms, and I will show you in the next slides, one of them that is called KT, that achieves this regret, that the black part is the optimal thing. It's exactly the optimal regret that you would have achieved if somebody told you what is the norm of x minus u. You have to pay a price, and the price for it is this logarithmic factor here. And we can also show that this logarithmic factor is optimal. And so, it's not that you can pay something smaller than that. If you don't want to know the future, that most of the time you don't want to know, this is the optimal thing that you can do. Okay, so how do we do that? So I have to say that I've been working on this problem for many years at this point, and I even gave a tutorial at ICML, and the tutorial was centered on a concept that I will show you in a moment between the connection between optimization, online learning, and betting algorithms. Now, I thought that this connection was really cool because it was showing the connection between two completely different fields, optimization and betting. And unfortunately, I couldn't convince anyone of this thing, in the sense that very few people actually took the time to study the proofs and go over the details. I will do another attempt today, but I thought that maybe there is a simpler way. Let's forget for a moment this connection that I will again I will show you anyway in a few slides, but let's forget about it and let's try to prove this thing from scratch. And so I thought, what is the simplest setting in which I can actually show you that parameter-free algorithms are possible and easy? You just have to do the analysis in the right way. So the setting is the following. You have a one-dimensional online convex optimization problem. You assume that all your subgradients are between -1 and 1. So this is Lipschitz 1. Now, this is the simplification. The feasible set is the non-negative numbers. Okay, so we are not on the entire real line, even if we're in 1D, it's just non-negative numbers. And this is the part that makes everything easy. I want to use this specific regularizer, okay? This is a convex function, so I can use it. I can use in FTRL. In FTRL, remember that I can have a regularizer that changes over time, so this is my regularizer. And I want to use FTRL with linearized losses. It's a weird regularizer, but it's a completely legal one, okay? I have that the regret of this algorithm is square root of t, 1 plus u log u, and a negative term that it doesn't matter. Now, I want to notice a couple of things here. This is a red term. So remember in the RGB notation that I showed you, the red term is the initial condition. Then there was the green term, that was the term of the gradients. There is no green term. The green term is 0 here. So the gradients disappeared. There is only the initial condition. And the initial condition, it's almost the optimal thing. The optimal thing would be u square root of t. That would be the optimal thing. You don't get u square root of t, you get u log u square root of t. Okay, this is not optimal. You should get u square root of log u, but this is good enough. Now, let's look at what is the update of the algorithm. The update of the algorithm is also very weird, but again, it's legal. So in each step, this is equal to exp or minus all the subgradients that you observed in the past, minus some term that depends on time. Okay. Let's gain some intuition on what's going on. Again, this is not gradient descent. This is not even online mirror descent. This is FTRL. So do not try to think in terms of step sizes, because even in FTRL, there are no step sizes. So what this algorithm is doing, suppose that all the GT are all the same, okay? What does it mean? I start from one place, and I'm keeping observing all the GT that they all have the same sign. It doesn't matter if they're the same or not, but they have all the same sign. It means that I am far away. I'm pretty far away from the optimum, right? If all the gradients, this is a one-dimensional function. If all the gradients they have all the same sign, I am really, really far away. I still have way to go till I reach the minimum. What happens in that case? This sum here becomes linear, roughly. And so x of t is exp of something linear, okay? And so what happens is that the algorithm is going exponentially fast towards the optimum. You don't get this behavior with any other algorithm. You don't get this behavior with online gradient descent, because in online gradient descent, each time you add your gradient, right? If each one of them is bounded by 1, even you using a constant learning rate, you move at a linear speed. But here you're moving at an exponential speed. Now, what happens instead if you are around the minimum? If you're around the minimum, you keep jumping from one sign to the other, right? So your gradients are changing sign. If the gradients are changing sign, this thing, it doesn't grow anymore. And so the jumps that you make are not exponential in time anymore, but you will actually converge to the optimum. Okay. And so let's compare this thing with online subgradient descent. Online subgradient descent, you had this problem of tuning alpha, and so you would get u squared divided by alpha plus alpha. And the impossible tuning, the one knowing u, would be absolute value of u, square root of t. Here, again, you get something very, very close to it, is this additional logarithmic term. And again, the optimal thing will be square root of log, so you are very, very close to it. But the important thing is that this is uniformly over u, and there is nothing to tune. There are no learning rates or nothing magic to do. This is always true. So let me try to do the proof. Why the proof is weird and why people keep not understanding this kind of algorithms? Because the regularizer that I showed you, this thing, it's not strongly convex. If you look at this thing, this is x log x. So it has some curvature. The log x is giving you some curvature, but it's not enough to give you strong convexity. Strong convexity says it should be a lower bound by quadratic everywhere in your space. This is not true. Okay, and so the classic analysis that I showed you, but basically says everything should be strongly convex, and then you will receive gradients, and the gradients will be divided by strong convexity. In this case, that term would be infinite, because if the strong convexity is 0, you get 1 divided by 0, you get infinity. However, here what happens is that green terms that are your terms that would be the terms that depends on strong convexity and gradients are 0. In each round, these terms are completely 0. Okay? And the proof is pretty simple, I have to say, and this is why I want to show it to you. How do you do it? I mean, this f of t is defined as the regularizer plus the sum of all the losses. And xt is exactly the minimizer of this expression. And so this ft_xt has this ugly formula here. It's not difficult to calculate it. It's just, I mean, this is just the derivatives, put it equal to 0 and solve for it. And so f of x of t is as this expression, f of t plus 1 xt plus 1 as this other expression, gt is just gt, and xt is the prediction of the algorithm that I told you what is the expression. Okay, and theta t is the sum of the gradients in the past. So this is the total expression that you get. Now you observe that this part here and this part here are the same, so you put them together. Okay, and now you have one inequality. There is one inequality in the entire proof. The inequality that you use is the fact that 1 plus y is greater than x of y minus y squared if y in absolute value is less than 1/2. Okay, and you use it here. You take this term here, your y is minus gt divided by square root of t. Okay, and for sure this is less than 1/2 because I assume that the number of iteration is at least 2. Well, I should have assumed more, probably. I should have assumed 4. I changed that. So if the number of iteration is at least 4, this thing here in absolute value is less than 1/2. So I can take this term and I can transform it into an exponential term. Okay, where I have this term with a minus, and the same term squared again with a minus. Okay, it's finished. The proof is finished because basically now I take this term, I add together with this other term, and I get exactly this term. I take this term, I add together with this other term, and I get exactly this term. And so that's it. This is 0. It's finished. So the green term in the FTRL proof, the one that depends on the gradient, the one that it's always square root of t term, that term is 0. And so in FTRL there were 3 terms: the red term, the green term, the blue term. The blue term, it's negative. It's always negative. The green term is negative. And so the only thing that remains is the red term. That's exactly this one. That is nothing else than the regularizer evaluated in U. And it's finished. Okay, I think I might, let me take a look. Let me do an additional slide. Now, at this point, you might say, okay, but I actually don't care because you went from this rate to this other rate. So the rate is still square root of t. Let me say that I'm doing online to batch conversion, so I'm actually using it to do stochastic optimization. I went to 1 over square root of t to 1 over square root of t. This is not a paper. Reviewer 2 will reject it because he will say, the rate didn't change. This is useless. Because it seems that you only improve the constant, not the rate, only a constant, right? Because this is a constant term. But not really. And to know why, you will have to wait to the second part. So welcome back. Now, I know that you just had lunch, and I know how hard it is to stay awake during this part of the lecture. So this part will be probably a little bit easier. That should facilitate the task for you to stay awake. But still there will be a lot of math. So I'm sorry for that. Okay, so we were here. We were at this part of the story. In which basically we improved the constant here from u squared to u log u, and we were wondering if this is good enough to be published somewhere. So the first way to answer this part is the following. If you ever used in your life stochastic gradient descent, you should know how painful it is to tune the learning rate. This is a very practical problem. And really, and the only way in which you can be sure to obtain the optimal performance is that you just try all the learning rates. You know, it doesn't matter how much of this adaptive stuff you use. At the end of the day, you just have to try all of them. And this is true, by the way, even if you use fancy algorithms like AdaGrad. So AdaGrad promises you to adapt to the learning rate, but it's not true because there is still an initial one that you still have to tune. And so the problem is still there. But you know, let's move for a moment from the applied world and let's go back to the theoretical world, and let me show you that it's not true that this is a constant. This is not a constant in a lot of interesting cases. So let's consider a very machine learning example. We are doing logistic regression on a data set of capital T samples. And so this is your objective function. So it's ZT are the features, these are the labels, and you just want to minimize this thing. And let's put ourselves in a situation that's actually pretty common. You have so many features that the data set is linearly separable. So this means that the minimizer of these objective functions does not exist because it's at infinity. So, I mean, mathematically speaking, the minimizer does not exist. The minimum does not exist. The infimum of this thing is 0, okay? So it doesn't matter that the minimizer does not exist. You still want to use your stochastic gradient descent to minimize this thing. And so this thing should go to infinity. So it should do something. I mean, you expect this thing to work. And in fact, it does work. And so more precisely what we assume that it's linearly separable with margin at least 1 by an hyperplane U star. So U star is not the optimal solution. Let me be clear about that. U star is just an hyperplane that is separating your data with margin 1. So if you use online subgradient descent with the averaging that I showed you before, you get this convergence rate. And now typically what you read in the literature is that they will put here X star, right? Where X star is the minimizer. So you are far away from the minimizer by a quantity that goes as 1 over square root of t. However, X star does not exist. Again, X star is infinity. So if you plug X star into this formula, you get something that is vacuous. So this is not the right way to write the convergence rate. The right way is exactly with that U that I insisted so much to keep it around for all the analysis. And so the right way to write your convergence rate is to say your, after capital T iteration, the value of the function in expectation is close to what? It's close to the minimum of this expression over U. So what is this thing? You are close not to the minimizer, not to the value to the infimum of f, but you are close to the minimum of f regularized by a certain amount that depends on the number of iterations that you did, okay? And this is already pretty deep because basically it's telling you, look, stochastic gradient descent does not need a regularizer. The regularizer is there. You are already close to a regularized solution. And I think this is very interesting. Now, this is already a non-vacuous guarantee, but it's not something that it's telling us something, because you would like to say, okay, the infimum is 0. How far I am from 0? This is what I care at the end. And so but this is the minimum over U. So this means that if I plug here any U, it doesn't matter, I will obtain some guarantee on my convergence rate. And so the U that I want to plug, I mean, by the way, it's possible to calculate exactly what's the optimal U, but it's kind of annoying. So let me plug something that it's good enough. I want to use U star logarithm of 2 times alpha divided by square root of t and norm of U star, where again, U star is the maximum margin separator. So if I put that expression here, this is f of u. So I put in f of u, and I have the average of the logarithm of 1 plus exp. Now, what happens is that I know that u is separating my samples with margin at least 1. So this means that this expression is at least 1. And so I can remove this entire expression and put 1 with a minus and with this constant term. Okay, so I have minus this expression. Then the other upper bound that I do is that log of 1 plus something is less than something. So I remove the logarithm. And here, this is x on minus log. So this is just the inverse of this expression. And I have t of them divided by t. So I just get this expression. Okay. So at the end of this entire thing, I get that f of u evaluated in this particular u as this particular value. That is 1 over square root of t. And so I can plug it back. And here I get now 1 over square root of t. Here I get 1 over square root of t. And here I get u squared. And u squared is this expression. And so you see that this expression now, it's not a constant. This expression depends on log t. And so first of all, I get that SGD is converging in this case. That is already good news because I would like SGD to converge. But again, if I just plugged here x star, this was vacuous bound. But instead, I get something meaningful. I get something like logarithm of t over square root of t. But the other thing that I get is that the u that I'm actually considering depends on time. So it's not a constant. If you gain something on the norm of u, you are actually gaining something on time. So it's not a constant anymore. However, you might say, okay, still, but it's a logarithm. We went from logarithm square to logarithm, not a big deal, I don't care. But this is a very simple example. Let me show something a little bit more complex. Let's now consider regression with kernels. This is, I know that nobody knows about kernels anymore because now it's all about deep learning. But 10 years ago, people were doing deep learning, were doing kernels. And kernels are still important from a theoretical point of view to analyze certain things. And so let me consider a universal kernel. Now, for example, a Gaussian kernel. What is a universal kernel? Universal kernel, it's a kernel that can approximate in the feature space, I can approximate any continuous function uniformly over a compact set. Okay, so if I use a Gaussian kernel, I can approximate anything. Okay, so I'm sure the Gaussian kernel basically is inducing an Hilbert space. In these Hilbert spaces, I have functions. And I know that among these functions, there is one that is arbitrarily close to any other continuous function that you want. Okay, so now I want to do stochastic gradient descent with kernels. I can totally do that. People used to do that. But now what happens is that even if it is true that your Hilbert spaces contain any approximation of your functions, it doesn't mean that any particular function is represented by function with a finite norm. This is not true. I can approximate it, but the closer is the approximation, the more the norm of your function might explode. Okay, so that I have a similar effect here, so that if I want to approximate a particular function, the norm might be infinite. And so again, I will have the same effect that again, the solution does not exist, and I have to do some tricks. And so now what will happen? What will happen is exactly the same as before. I have this minimum over u. But now u is in this Hilbert space is induced by your kernel. And I have this f of u that is my regression function within the kernel space. I have the norm of u measured in the Hilbert space. But now this thing, this object, it's known to have a certain behavior that is t to the minus a, sorry, this should be a, where a measure how smooth is the optimal solution. Now, there are tons of references on this topic, but if you were yesterday attending the lecture by Taji on deep learning theory, at a certain point, Taji mentioned exactly this effect. If you're doing regression in reproducing kernel Hilbert spaces, and you know that the eigenvalues are going to 0 with a certain rate that depends on A, now you will know that the optimal rate will be something that depends on A. However, Taji sort of, was hiding some details on this thing. It is true that the optimal rate will depend on this decay of the eigenvalues, but in order to obtain that, you have to choose your regularization in the right way, or in alternative, this is what he was doing, you have to truncate your solution to a certain number of bases. So there is something that you have to know in order to tune your algorithm. Okay, this is unavoidable. However, now, what is the alternative? The alternative is that now you can use, so what is the first consequence? The first consequence is again that the norm of u here is not a constant. It's not a constant, and here it's not logarithmic in time. Now it's something that will be polynomial in time, where the polynomial will depend on this A that measures how smooth it's your solution that you're looking for. Now, what happens if you use one of these parameter-free algorithms? This means that you can run stochastic gradient descent, one pass over your dataset, nothing to tune, and you can show that the optimal solution will depend optimally on this smoothness parameter A, but you don't have to tune anything. You don't have to tune a regularizer. You don't have to tune a learning rate. You don't have to choose how many bases you want. The entire thing is automatic. You get the optimal rate. Okay, and so you're not really gaining just a constant. You are getting the optimal rate for free. So this is the actual real message of parameter-free algorithms. Okay, so let me show you a brief history of parameter-free algorithms. Let me show you what is this coin betting view that will allow us to go beyond that very simple example that I showed you that was just one-dimensional, just non-negative numbers, to something that works actually Hilbert spaces, Banach spaces as well. So this entire field of parameter-free algorithms started from a single paper. It was NIPS 2012. Brendan McMahon and Matthew Streeter that basically showed that this thing was possible in one dimension. It was possible to obtain the right bound in one dimension. That is very, very close to the bound that I showed you, by the way. But if you read the paper, it's very clear that the author themselves were not understanding what they were doing. I mean, they obtained this thing. It was very new, and it was unclear even to them what they were doing. And then there was a sequence of paper between them and me, and also together, in which we hammered down the details until we obtained the optimal bound. Optimal bound, Hilbert spaces, so any number of dimensions. And it's always the same trick. I want to stress that this entire line of papers, they are all based on the same trick. It's always FTRL. It's always a very specific form of the regularizer and that we change until we arrive at the correct one. But all these proofs are very, very complex. I mean, the one that I showed you, it's 3 lines. But in general, if you want to do the general analysis, it's very, very complex. And so in 2016, we obtained this coin betting view that, again, it's the same idea, but just simplified, if you want. And there was nothing new, nothing really new, up to 1 year ago, where people discovered that it's possible to obtain a slightly better bound if, instead of assuming that things are adversarial and then using an online to batch conversion, you assume from the beginning that things are actually stochastic. If you're assuming that you're doing stochastic optimization from the beginning, instead of having something, instead of the penalty that you pay for not having a learning rate, instead of being logarithmic in the norm of U, can be log in the norm of X star. Okay, and by the way, it's unclear if this method extends to cases in which the minimizer does not exist. But still, this is a breakthrough because it shows a gap. It's not really important that you go from log to log. The algorithm is essentially the same. But the point is that it shows a gap between the adversarial world and the stochastic world. And this is one of the few cases in which there is a gap. And you can see that even in this case, the gap is really, really small. Okay, so let me show you what is the actual way in which now we design this parameter-free algorithm and how does it work. The key idea actually goes through duality. The same duality that Marco was talking about in this morning, but the difference is that typically optimization people talk about duality on the problem. You have an optimization problem with constraints and you construct a dual and then you solve the dual and then from the dual you recover the primal and so on. Here we want to do something a little bit different. We will apply duality on the convergence rate of the algorithm coupled with the problem that we are solving. Okay, so it's not duality on the problem alone, but it's duality on the problem together with an algorithm. Okay, it's very, very different from the usual duality. Okay, so how does it work? Let me redo the first steps of the online to batch conversion. So you want to minimize a fixed function f. And we know that we want to prove that the average of iteration minus f in any u is upper bounded by something. So again, this is a Jensen inequality. And the other step is just the fact that GT are subgradient of F. Let's consider just deterministic. So this is exactly the subgradient of F. Okay, so these are the first three steps. Good. We are at this point. Now here, we would like to say, this is small, right? We would like to say, look, this is really small, and this depends optimally on the norm of U. This is what you want to say. However, the difficulty arises from the fact that you don't know U. This is exactly the problem. You don't know U. U is unknown. How do you do that? So this is a very small and simple lemma, but I will not prove it, that basically says, every time you want to prove that there exists an algorithm that produces xt based on the previous subgradients, such that this is less than any convex function of U, and this is true for any U, okay, because this is what you want to prove at the end. You would like to prove this is less than norm of U square root of t. This is your objective. Now, you would like to prove this, but this is difficult. Instead of proving this is completely equivalent to prove a dual objective. And this dual objective says, instead of proving this, prove that minus inner product between the subgradients and xt is greater than the Fenchel conjugate of this function evaluated in minus the sum of the gradients. Okay. Now, again, these are equivalent. These are completely equivalent. So you can show one or the other, it doesn't matter. But one of the two, it's easy, and the other one is difficult. This one is difficult because it depends on U. And so this one, if you actually want to show that this has the optimal dependency on U, you have to craft an algorithm that somehow has this knowledge of U that it's difficult to do. This other inequality, there is no U. There is nothing that is unknown in this inequality. Everything is known. The subgradients are known. The x of t are the one that the algorithm is constructing. Psi star is just the Fenchel conjugate of the function psi that you are trying to prove. So again, it's known. It's something that it's given to you. And so in this inequality, everything is known. And so this is a much easier thing to prove than the original one. And that's it. This is the entire trick. Okay. And by the way, the proof is really, really easy. It's really a few lines. Okay, so how do we use this technique? We use it in this way. Let's assume that, again, everything is Lipschitz. The subgradients are bounded one by one. And let me give you the algorithm. I give you the algorithm. This is the algorithm that you want to use. You want to do stochastic gradient descent. Instead of doing stochastic gradient descent, you use this kind of prediction. This is minus the sum of the stochastic gradient from 1 to t minus 1, divided by number of rounds plus 1, because there are t minus 1 rounds, you divide it by t, okay? And then you multiply this thing by a number. This is a number. And this is 1 minus the inner product between the subgradients and the iterates. That's it, okay? Now, this is not stochastic gradient descent, but this is as simple as stochastic gradient descent. It has exactly the same computational complexity. If you can implement one, you can implement also this one. Now, I claim that this algorithm guarantees you that minus GTXT is bigger than some function psi star of minus the sum of the gradient for any sequence of gradients. And what is this particular psi star? This particular psi star has more or less this shape, okay? Now, let me go back to the previous slide. If you show this, now automatically you show that this is less than the Fenchel conjugate of the function. And then you plug it back here, you get your convergence rate, just divide everything by capital T. Okay. So this is the function. We just have to calculate the Fenchel conjugate. We can easily do it. How did I do it? I asked Wolfram Alpha to do it for me. This is exactly how I did it. And you still get a very nasty formula, but you can upper bound it so that you can get something nice looking. And this is your psi, the Fenchel conjugate of this function here. And that's it, it's finished. The proof is finished, okay? So now the only thing that remains to be done is to say, wait a moment, where this algorithm comes from? How were you able to prove this inequality? It seems that, you know, it seems very surprising. The algorithm is very different from the usual ones. So first of all, this algorithm is FTRL. I know that it doesn't look like FTRL, but there is a way in which you should be able to see that this is immediately FTRL. If you look at all the gradients, they all appear with the same weights. Immediately, you should think this is FTRL. There is no other way that this is another thing, okay? It's a weird form of, it will have a very weird regularizer, but it's still FTRL. However, again, as I told you, it's difficult to see as FTRL. Let me show you what was the way in which I derived this algorithm. So there is a problem, a classic problem in information theory. Now, you should know that information theory, one of the things that they study is compression of bits, arbitrary bits. They are not coming from a distribution, right? It's a file, so there is no reason to believe that this is coming from a distribution. You are seeing all these bits one after the other, and you have to compress them. There is now another thing that you should know. Compression and gambling on a coin are exactly the same problem. If you read the book by Cover about information theory, there are a couple of chapters in which it will explain you that if you can do compression, you can do gambling. If you can do gambling, you can do compression. It's exactly the same problem, okay? So this means that information theory people were solving at the same time two problems. They were solving this compression problem, but they were solving also this betting problem. Let me describe you what is the betting problem in particular. You have a sequence of, let's not say that there are bits, there are coins outcomes. And instead of saying that it's just a coin that will give you just a +1 or a -1, it's what I call a continuous coin. So it will give you a real number between +1 and -1 in each round, okay? And what you have to do is that in each round, you have to bet money, okay? It's like the roulette. You are basically betting on red and black, but now just instead of being just two outcomes, you have basically all the colors between, red and black, the continuum. And you start with $1, and your aim is to make as much money as possible. There is only one rule. You cannot have negative money. So you can always bet as much money as you have. You cannot bet more money than what you have. And now in each round, what you do is that you win or lose the money that you are betting, multiplying the outcome of the coin. Where the money that you are betting, they have a sign because the sign is codifying on which side of the coin you are betting. Okay, so if I say that I bet 0.3, this means that I am betting 30 cents on +1. Okay, if I bet -0.3, this means that I'm betting 30 cents on observing -1. Okay, so that if the product of these two has the same sign, you win money 1-to-1. If, like at the roulette, exactly the same. If they have the different sign, you are losing money. Okay. Now, again, this is a known problem, and it was solved by information theory people. And information theory people tell us that what's the optimal strategy? Or let me be a little bit more precise. What's one of the optimal strategies? There are many. This is the simplest one that I will describe. It says in each time step, you look at the outcomes in the past, and you just sum all of them, and you divide it by number of rounds +1. That is a fraction with a sign, because again, it tells you on which side you should bet. It's the fraction of money that you should bet in the round T. Okay, that's it. This is the optimal thing. How do we know that this is optimal? Because the amount of money that you will make using this strategy will be this exponential quantity. Okay, so let me stress a couple of things. This inequality here on the screen, it holds deterministically. This is a deterministic inequality. And we are not assuming anything on the outcomes CT. This holds for any sequence of CT. This is always true. And why this is a good thing to have? Because let's assume that the coin is biased. Again, it doesn't matter how it is generated, but let's say that the positive side is appearing more often than the negative side, so that this sum here is slightly positive and it's proportional to the number of rounds. So you get something proportional to t. This is t squared divided by t, so exp of t. So if you use this strategy, this term is exponential in time. And this is exactly what you would like to have. You would like to have your money growing exponentially over time. What is this other term here? This is a polynomial term that is the price that you pay for the fact that you don't know in advance what's the optimal fraction of money to bet. Okay, so this is the price for not knowing the future. And this is possible to prove that this is optimal. The square root of t is optimal. The only thing that can be improved is the constant 2. And it's not even worth trying doing. And so again, if the coin is biased, you win an exponential amount of money and you pay only a polynomial price for not knowing the future. Okay? It's a very powerful strategy to keep in mind if you ever want to, play the roulette. Now, remember what was our objective? We did this brief detour because I just wanted to show this inequality. This is the inequality that I need in order to do convergence rates. Now, let's look at this inequality here and let's see what we want to prove. These are basically the same thing. I just have to do one tiny thing. The sign is not correct. So let me assign coins equal minus gradients. The gradients, I assume that all of them is bounded by 1. And this function psi star turns out to be that exponential function that I showed you before. That's it. It's finished. This is the way in which we derived the parameter-free algorithm. We took an algorithm from information theory. It was already, perfect, optimal. And by the way, look at the algorithm. There's nothing to tune in this algorithm. There is no learning rate, nothing, no prior, no regularizer. This is parameter-free. The algorithm is optimal. People already proved before us that the algorithm is optimal. And the only thing that I had to do is just to say, oh, let me do, coins is equal to minus gradient. Let me calculate the differential dual. And I obtained the optimal convergence rate. Okay. Now, the caveat, this entire reasoning is that this entire thing works only in 1D. And so this was our contribution to say, if actually the entire proof that they did, we redid it in the Hilbert space cases, and it still works. You still get exactly the same thing, so that you will get everything with norms here instead of absolute value. Okay, so this is the connection between optimization and betting and compression. Okay, so. And again, let me show you again the algorithm so that you remember how simple it is. Now, I want to stress that, and this is what we called KT. We call it KT because this strategy is called Krzyzewski-Trofimov. And this is a very well-known strategy in information theory. One thing that I want to stress, if you actually look Krzyzewski-Trofimov on Google, you will never find anything related to betting because this is a compression algorithm. People design it as a compression algorithm, but again, compression and betting are the same thing. And let me show you where is Krzyzewski-Trofimov hidden in this thing. This is exactly the sum of the coins divided by number of rounds plus 1, right? Because the coins are minus gradients. So this is exactly the fraction of money that Krzyzewski-Trofimov is telling you to bet. What is this thing? This is the amount of money that you have now. Why? This is your initial dollar. And this is how much money you won or lost till now. So this is your current wealth. And this is the fraction of money that you should bet. So this is exactly Krzyzewski-Trofimov applied to do optimization. Now, again, this is the basic version. We have a lot of more refined version. I also published at a certain point an algorithm that was specific to deep learning. But a couple of things that are more interesting from a theoretical point of view. This entire thing assumes that the functions are Lipschitz and you should know the Lipschitz constant. But there is a paper by Ashok in which he removed this assumption. So there is a variant of the algorithm in which you don't have to know the Lipschitz constant. It works in any number of dimensions, Hilbert spaces. We also have a variant that works in Banach spaces. It works with stochastic subgradients as it is. Nothing changes. The algorithm as it is works if these are stochastic subgradients instead of being subgradients. And it works also with constraints. If you have constraints, in this paper, we have a generic reduction that allows you to take any algorithm that is designed from unconstrained optimization and transform it into one that is for constrained optimization. And so it's for any algorithm, it's also for these algorithms. And by the way, again, this fact that you are adaptive to U will imply a lot of things. Before I showed you that it will imply, for example, that you can basically have optimal rate in reproducing kernel Hilbert spaces, but there are a lot of other consequences. For example, we can show that through another reduction, if the functions are strongly convex, you adapt to the strong convexity for free. You don't have to know the strong convexity, automatically you will get the optimal rate. Okay, so let me move to this other part that I think is the interesting part. Now, when people think about online convex optimization, they think about losses and regret, basically what I showed you till now. And even worse, they think about bandits. That, sure, they're very, very interesting, but there is so much more, so much more. And you know, the interesting thing to me is that online learning at the end, intrinsically, it's not about losses and regret, but it's about proving inequalities on any sequence of vectors. This is the core of online learning. And this core can be used as a lot of other applications. And in my opinion, the inequalities that we get are actually more important than the algorithms themselves. And so I'll try to convince you of this view here. And so the first application that I want to show you is how to use online convex optimization to do non-smooth, non-convex optimization and obtain optimal guarantees. Okay, so first of all, this is non-convex optimization. So in convex optimization, we typically, till now, basically, I showed you that you study suboptimality gap. So how far I am from any vector U. And we can do it because the function is convex. Sooner or later, I will minimize this thing. If the function is non-convex but smooth, what typically people study is how fast the gradients are going to zero up to some randomization, because you cannot guarantee that the last gradient is going to zero, but you can guarantee that the gradients are going to zero because you're basically converging to a local minima or to a saddle point, to a place that is basically flat. And you can do this because the function is smooth. So a smooth function, when I approach a minimum, the gradient is also going to zero. Now, if I am considered a function that is non-convex and non-smooth, this is not true. I cannot analyze suboptimality gap. I cannot say that the gradient is going to zero. And this should be clear from this function. Now, this part is convex, but you can imagine that here there are other parts that are non-convex that makes this entire function non-convex. And when I am in any part of the function, the norm of the gradient is always the same. It's always 1. And so the gradient is always 1, and then there is one point in which it's non-differentiable, and I can imagine that it's basically 0 there. It's only one point in which the gradient is 0. Anywhere else, it's 1. So I cannot really say the gradient is going to 0 because it's not true. Okay, so I need another way to study the fact that I am converging to the right point. And the right notion, or at least the more modern notion, is the one that was proposed by Zhang et al. From MIT. They basically proposed this very different notion. And let me describe you in details this idea. So he defined the notion of delta epsilon stationary point of an almost differentiable function, where the following happens. Okay, so this is your function. You return a point x, and you would like to say, sure, the gradient is not 0, but basically I am very, very close to the right point. Okay, I want to convey this information. How do I do that? I have to guarantee that around x, there is a distribution of points such that when I take the average gradient with respect to this distribution, the average gradient is small. Okay? And so why this is a good point? Because if I take, for example, x1 and x2, and these points, by the way, they have to be at most delta away from x, and this is exactly the delta here. If I take these 2 points and I take the average of the gradient here and the average of the gradient here, the average of the gradient is 0. Okay? And this basically codifies for the fact that this is a good point. And this works, by the way, because first of all, the definition makes sense if delta is small enough. If delta is really large, it's not capturing anything. But if delta is small enough, this is true because x is close to the minimum. If I move x here, and if I am delta away from it, the only points that I can take will make the gradient always on average 1. But the moment that I approach the minimum, I can make the gradient small. Okay, makes sense. Okay, and so again, it is delta epsilon stationary point. If I can select points around it at distance at most delta, such that the average gradient according to this uniform distribution over these other points is at most epsilon. Okay. Now, we have to select what are the functions that we want to analyze. It's non-convex, no smooth, but we need something. So we constructed this definition that we called well-behaved. Well-behaved, it's a very, very weak thing. Basically says your function should be nice enough so that the fundamental theorem of calculus holds. So that the function can be written as the integral between 0 and 1 of the gradient on the line segment between x and y, inner product y minus x. Okay, this is the fundamental theorem of calculus. In 1D, I think you saw it before. Basically, in 1D, this says that the integral is the inverse of the gradient, and this is in multiple dimensions. Now, up to perturbing the function with some noise, if the function is locally Lipschitz, this holds. Okay, so this is very, very weak, and this is the weakest thing that we could use. And by the way, this also holds for ReLUs, because we were exactly aiming at the non-convex functions that are found in neural networks. If you take a neural network and you calculate what is called the directional derivatives, this property will hold for the functions in a ReLU. Okay, so let me show you immediately the algorithm. The algorithm is the following. You need an online convex optimization algorithm that you will use as a black box. Okay, you don't even want to know what is inside. You just need to know that it has a regret. And the algorithm goes on in cycles of length capital K, and you also need the usual initial point. Okay, so what do? In each cycle, the first thing that you do at the beginning of each cycle is that you reset the online convex optimization algorithm to 0. You erase completely its memory, and it starts completely from 0. You also start from 0 this vector here that will contain the average of all these xt prime over your cycle. Okay, again, the cycles is capital K iterations, and so this thing contains just the average of these vectors, and you initialize it to 0 at the beginning of each cycle. And J is just an index for this thing. Now, what do? How do you use the online convex optimization algorithm? Now, you would be tempted to say, okay, I have an online convex optimization algorithm. It is an optimization algorithm. Whatever the optimization algorithm tells me to it is xt, I query the gradient on xt, right? This is the normal thing that you would do. This is stochastic gradient descent kind of approach. But instead, it's not the right thing. Whatever the algorithm tells you to do, that is not the point in which you query the gradient, but instead that is the update. So the online convex optimization algorithm gives you a vector, let's call it MT, and you update with MT. Okay? So the online convex optimization algorithm constructs the update for you. Okay, now, so this is your new iteration xt. Now, you would like to query the gradient on xt, but again, this is not exactly what you need to do. Instead of taking the entire step MT, you take a learning rate uniformly at random between 0 and 1, and you construct this other update here, xt prime, where it is xt minus 1, where minus this stmt. Okay, so it's not the full update, it's just a scaled version of it, where this learning rate here is stochastic. Finally, you query the gradient on this point, and you construct a linear loss using this gradient. Okay, everything is deterministic here. So this is a linear loss. It's convex because it's linear, and you pass to the online convex optimization algorithm. The online convex optimization algorithm will do whatever it wants to do, and it will give you in the next round the next MT. That's it. This is the entire thing. Okay. Okay, so what we can show? We can show that if the online convex optimization algorithm is just online gradient descent, the plainest thing possible, it's just online gradient descent with a constraint of an L2 ball of radius d, then we can show that this ugly expression that we will parse in a moment is less than the difference between f of x0 and the infimum of f, divided by t, capital T iteration, and 1 over the square root of the length of the cycle. Okay, again, in a moment I will tell you all about these terms. Now, the theorem also says that if you set d equal to delta over k, and k also has this particular choice, and you take one of the xj bar, where the xj bar were these ones that you were constructing, one for each cycle, so you have a bunch of them. If you take one of them at random, in expectation, this thing is a delta t delta to the minus 1/3 stationary point. Okay, so first of all, this is optimal. And this is the first algorithm that achieves this optimal rate. Now, let me show you a little bit more in details what's going on. So first of all, where the choice of d come from? Why I have to choose d equal to delta over k? Because if I choose d equal to delta over k, I have that, given that the algorithm is generating the updates for me, and given that I am telling the algorithm is on line gradient descent on an L2 ball of radius d, and so each update, the norm of each update is at most d, okay? So this means that this vector is an average of k points, and the distance between the average and all of them is at most delta, okay? And this is important because remember the definition. The definition of delta epsilon stationary point says I return a point and I have to prove that there is a distribution of points around it at distance at most delta. These are exactly the points, okay? The points in the cycles are exactly the points on distance delta. Now, once I have chosen d, this expression here becomes this other expression. Just substitute d with the value of t that I have here. Now, this expression is expression in k, right? How do I choose k? I choose k in order to minimize these terms. And this is where this choice of k comes from. Okay? I want this sum to be as small as possible. And if I choose this, this setting of k, I will get that this expression here is exactly the expression here. Okay, so this t delta to the minus 1/3 is the minimizer of this with respect to k. Okay, so we know where this term comes from. It's just the minimizer of this with respect to k with a choice of d. Now, what is this ugly thing here? Okay, so there are two averages. There is an average over the number of cycles that you have, because you have capital T iterations. Each cycle has length k. So how many cycles I have? T divided by k. Okay, so this is an average over the cycles. What is the stuff inside? The stuff inside is the average gradient over the cycles. Okay, over each cycle, I have a bunch of iterations, and I am looking at the average value of these gradients. Okay, so now if I take one of the cycles at random, I can basically take this expectation here and put it together here in the randomization. Okay, this is the usual trick of taking one iteration at random. And so this expectation here is equal to this, where now J is one of these cycles at random, uniformly at random. And so this thing now it's equal to exactly to this expression here. And so what this expression says, I return one of the xj at random. I can assure you that in expectation, there are k points around it at distance at most delta, such that the average gradients on top of them is at most epsilon. Okay? And so I constructed the distribution, and I assure that this distribution has average gradient that is small. Okay, so let's see the proof. So first of all, I have to go from function value to gradients. This is essentially in any optimization algorithm. And so for convex function, I use the fact that I can construct linear lower bounds. For non-convex smooth functions, I can construct quadratic lower bounds. This is also a classic result. What can I use for non-convex non-smooth? And this is the new trick. I mean, it's new in the sense that it was used even in the original paper by Zhang. So where we evaluate the gradient in that weird randomization thing. And so we can rewrite the weird randomization as MT, what is the output of the online convex optimization algorithm, that is also equal to xt minus 1 by the update that I do. Okay, so this is exactly. Now, ST is a number or stochastic number between 0 and 1, uniformly taken uniformly on uniform distribution of 0, 1. So this means that if I take the expectation of with respect to ST of the gradient of f in xt prime, this is the gradient of f in xt minus 1, this thing, plus t, this other thing, and then I take the expectation. So it's just the integral between 0 and 1. This is the uniform distribution, and so that's it. Okay? This is the expression of this expectation. Why this is useful? Because I said, I assume that the functions are well behaved. So they satisfy the fundamental theorem of calculus. So this is true. Now look at this expression here. This expression here is exactly this. That is this thing. That is equal to the expectation of the gradient in xt prime. This is my link. I was looking for a link between function value and gradients. I have it. This is a very strong link because it's with equality. It doesn't need convexity. It doesn't need smoothness. The only caveat is that I need to sample the gradient in a weird point because it's a stochastic point, but that's it. Okay, so this is our main trick. How do we use it? And this is the proof, the usual one slide of proof. So f of xt minus f of xt minus 1 for what I wrote in the previous slide is exactly this, the inner product between this expectation and this other point. These points are equal to minus mt by definition of the update. And now let me add and subtract any vector u. I can always do that. So now what I do is that I take full expectation. So this thing goes outside. And I sum over all the iteration in the first cycle. Okay, let's consider one cycle at a time. This is only first cycle. And I consider any vector u that is less than d. And so I have the sum of the first terms, where the expectation went outside, the sum of the second terms, again, expectation outside. What is this guy? This is exactly the regret of the online convex optimization algorithm with respect to u, because these are the losses that I am passing to the online convex optimization algorithm. So this is exactly the regret after capital K iterations with respect to u. And how much is this? Well, I immediately know how much is this because I'm using online gradient descent. The domain is k, the diameter is d, so this is d square root of k immediately. Okay, I don't have to prove it, I already know. This other term is still the same. So at this point, this equality, and by the way, this is a telescopic sum. This is why I get the last and the first. So at this point, this is true for any u where the norm is less than d. Which u I want to choose? I choose exactly the sum of these terms here divided by their norms, so that this is a vector on norm 1 multiplied by d. Okay, so that this term here becomes minus d norm of the sum of these gradients. And this is exactly the stuff that was appearing in my proof on the left-hand side. So now this was one cycle. I just have to sum over the cycles. And again, this is a telescopic sum, so this will keep telescoping till the end. This thing will just be multiplied by the number of cycles that I have. And this thing will just be summed over the cycles. And then I divide it by d, capital T, and I get my theorem. Let's look at the theorem again. This was the sum of the gradients. This is the sum over the cycles. And this is the telescopic sum. And this is my regret term. That's it. So I know that it's a lot to take, but it's still one slide. Okay, so if you look in the paper, by the way, there are other results. And what we showed is that apart from the fact that this is optimal, it was the first time that people obtained the optimal rate. These also extend to the stochastic setting, same rate. You can also assume that the functions are smooth, and you can wonder if this reduction still works. And it still works. You get the best rate of SGD. You can also assume that it's smooth and deterministic. Again, you match the optimal rate. And very recently, there is a paper on arXiv in which, like a month ago, in which people basically try to use this framework to look at Adam. And they basically show that you can recast Adam in the same way, so that Adam is the same thing. It's an FTRL algorithm that is giving you the updates. And speaking about Adam, let me show you what is the final algorithm that you get. So that I want to show you that the algorithm that we get is reasonable. It's not something crazy. So again, the update that you do is x of t minus 1 minus mt. Mt is given by online gradient descent. What is online gradient descent on a domain of radius d? This is online gradient descent of a domain of radius d with the losses that we are using. So we take mt plus learning rate gt. There is a plus because the losses, they add a minus. And then you have to do the projection over d. Let me call projection clipping, because this is basically clipping. And this is the reason, by the way, I call it this thing m, because you can look at this thing as a momentum term. So the final algorithm basically says, calculate a momentum term, clip each one of them, and use it for the update. The only weird thing in this algorithm is that instead of querying the gradient xt, you query the gradient in a perturbed version of xt that depends on this stochastic st. That's it, but it's the only weird part. The rest is a very, very natural algorithm. So even if we went through this online to non-convex conversion, at the end of the day, we got an algorithm that is natural for deep learning people, at least. Okay, so let me move quickly to the other part. Let's try to take questions at the end, because I don't know if I'm able to do everything. Let me show you another example. Again, I want to use online learning to do something that is completely different. This is a classic problem in statistics. I want to estimate the mean of a random variable. The random variable is in between, this is a sequence of random variable in 0, 1, and the only thing that I know that is that the expectation condition on the past of each one of them, it's mu for each of them. And I want to estimate mu, and I want to give confidence interval that holds uniformly over time. So basically, I want to give you a sequence of interval ATBT, such that the probability that mu belongs to ATBT for all dt, this is the uniformity, is at least 1 minus delta. Now, of course, this is very simple if I just state it in this way, because you could say the interval is just 0, 1, 0, 1, 0, 1. It's always 0, 1, because for sure it contains the mean. So I ask something more. I want the width of the confidence interval to shrink to 0 at the optimal rate. That should be sigma over square root of t, roughly, where sigma is the variance of the random variables. Now, what's the classic approach? The classic approach is that you take an average of the random variables, you use a concentration inequalities, and you use a union bound to have uniformity. And for example, you use Mauer and Pontil, and you get that the true mean is the estimated mean plus or minus something that goes as sigma over square root of t with high probability. Okay, this is a classic result. Everything is optimal here. Apart from the fact that you should get log t instead of log t, everything is known. Now, what's the caveat? Why I'm even describing you this problem? The caveat is that if you actually use this thing, and if you actually care about the numbers that you get, this is not a theoretical problem anymore, this is a practical problem. Most of the time, if you don't have enough samples, the estimates that you get are vacuous. This is the same thing, by the way, in deep learning, when people say, oh, all the generalization guarantees that we have, if you evaluate them, you get something vacuous. It's exactly the same problem. If you don't have enough samples, you get confidence intervals that are bigger than the original interval of 0, 1. And so they are useless. However, ideally, it should be possible to construct an algorithm that gives you confidence intervals that are always non-vacuous, in the sense that are always strictly less than 1, even with one sample. And this is what we will do. Okay, so I will do it. I will use a betting algorithm to derive concentration inequalities. And again, this is very, very simple. This is less than a slide. So how do we do that? What the concentration inequality says? What is the meaning of a concentration inequality? Concentration inequality says, if I take many, many, many random variables, IID, let's say, and I take their average, these empirical average cannot be too far from the true average, right? Now, let me instead tell you something about gambling. This is called Will inequality. Will inequality says, if you're betting money on a fair coin, it doesn't matter which strategy you use. The only thing that we assume is that your money never becomes negative, but then you can use any strategy in the world. Then the probability that the maximum amount of money in any moment in time is big, it's small. Okay? So this basically says that, you would like, people think that if you play at the roulette and if you stop at the right moment when you are winning, you will win a lot of money. No, Will says no. The probability that this thing will happen is really, really, really small. It can happen, but it's really small. Okay. And by the way, why Will proved this thing? Will was the guy that invented martingales. And he invented martingales because he was talking about betting. And so if you read, this was his PhD thesis. If you read the entire PhD thesis, it's about betting. And he was trying to use betting to try to find a way to define randomness. So he found a way to link betting and probabilities. And so he was really talking about wealth. This is not, a metaphor. He was really talking about wealth. So now let's put these two things together with the stuff that I showed you in the previous slides. So you start with $1 and you use a betting algorithm to bet on the outcome xi minus mu. Now you just imagine to do it. Why you have to imagine? You don't have really to do it because you don't know mu. You're trying to estimate the true mean, so you don't actually see this thing, so you can actually run the algorithm. You just have to imagine to do it. Now, which algorithm we want to use? We can use any algorithm. Let me use Krzyzewski-Trofimov, the one that I showed you before. Krzyzewski-Trofimov says your wealth will be at least this quantity, where these are the sum of the outcomes of your continuous coin. And it doesn't matter how the continuous coin is generated, this is always true deterministically. Okay? Now, that's it. We have all the ingredients to prove our concentration. So let's start. Will inequality says, doesn't matter what you do, you will never gain money. Now, this holds for any betting strategy. Which betting strategy we want to use? Let's use Krzyzewski-Trofimov. Krzyzewski-Trofimov says your wealth is at least this quantity. So this is a lower bound. So this gives us a lower bound to the probability. And so now we have the probability that maximum over t of this expression, that is this lower bound by Krzyzewski-Trofimov, that is bigger than 1 over delta is less than delta. It's finished. You just have to solve this inequality here to put it in a slightly nicer form. And so you get the probability of the maximum over t of the deviation between the mean and the empirical average. This is the probability that this is bigger than roughly 1 over square root of 1 over t is less than delta. Or if you want, you can write it as with probability 1 minus delta, the deviation is at most roughly square root of 1 over t. Okay, so we use the fact that a betting algorithm guarantees you a certain wealth to prove a concentration inequalities. And this is true for any betting algorithm. Every time you have a betting algorithm that guarantees you something, this corresponds to a concentration inequality. Now, this concentration per se is not very interesting because basically we got Chernoff bound with a worst constant. But we used an algorithm that is good, but not the best. So now, before telling you what is the best algorithm, let me tell you that this is not my idea. There is an entire field in which people try to link gambling and probabilities. This very recently, there are 2 books by Schaefer and Bobk, 2 entire books on this topic. They're not really easy, I have to warn you. But they basically say the entire field of probability the core should not be measure theory, but it should be gambling. And they basically are the first ones that recently proposed this idea of proving concentration inequalities, or more generally, testing. Any kind of statistical test should be rephrased as a betting game. And they do this because you will actually gain a lot of advantages in doing this. This is not just for fun, but actually practically you will gain advantages. Recently, Hendricks was the first one to evaluate numerically this thing and to say, oh, numerically, if I actually use a betting strategy to derive confidence intervals, numerically, these confidence intervals are really, really good. They're better than state of the art. And more recently, while this meter randomness, and this is a paper that got a lot of visibility, said, the right betting algorithm to use are just heuristics. Let's define a lot of heuristics. In their paper, they have a bunch of them. And their motivation was, theory will never be as good as an heuristic. And so, it doesn't matter what's information theory people say, I will design a fantastic betting heuristic, and this will give me very tight concentrations. On the other side, me and Huang in 2019 were the first one to show that a regret guarantee of a betting algorithm can be transformed into concentration inequalities immediately, and this gives you new concentration inequalities. And we were inspired by the paper of Sasha and Kartik, in which they proved something even more powerful. They proved that any online learning algorithm is equivalent to a concentration, in the sense that it goes both ways. Every time you have a regret, you have a concentration. Every time you have a concentration, you have an algorithm and a regret. Okay? But in their paper, they were not using Wheeler inequality because they didn't have betting algorithms, so they couldn't do it. And so their proofs are very, very difficult. The proof that I showed you, it's really, really simple. But if you want to really find the first person that described this idea, you have to go back to Cover. This is a technical report, probably a rejected Annals of Stats, because it's written in the footnote submitted to an Annal Stats, and it's not in any Annal Stats, I looked, in which he was the first one that he recasted a statistical test as a betting game. And he also proposed what was the optimal strategy for the betting game, because Cover was the information theory guy that knew everything about betting. He knew the link between compression and gambling, so he knew this kind of things. And Cover is important because it will be also the one that created the optimal betting algorithm. So what is the optimal betting scheme that will give us the optimal concentration? The optimal betting scheme is universal portfolio by Cover. So what is universal portfolio? Universal portfolio is the online algorithm that you should use if you want to invest in the stock market and you believe in online learning. Basically says in each day, the algorithm will tell you how you should allocate your money over a number of stocks. And so you buy all these stocks. At the end of the day, you sell them. You pass the information about how much money you made to the algorithm, and the algorithm next day will tell you what to do. Okay? And you keep repeating this. So you buy and sell each day. Universal portfolio assures you that your log wealth will be a logarithmic factor away from the log wealth of the best constant rebalance portfolio. Okay, the best constant rebalance portfolio is a portfolio in which each day you buy and sell the stocks, and you always buy with the same distribution of money on the same stocks. So you keep this thing constant with the knowledge of the future. And so you are a logarithmic factor away in log wealth. And this is the optimal thing. So if you use a universal portfolio with two stocks, the problem that I showed you of betting on that continuous coin can be solved optimally. And so what we can show now is that this expression, this weird expression with probability at least 1 minus delta is log 1 over delta plus the regret of the algorithm that is log square root of t. Now, this is exactly the same reasoning that I did before. It's again Wheeler inequality, and it's again the wealth guarantee of an algorithm. But the difference with before is that I cannot invert this thing. I cannot symbolically invert it and show you a concentration that says, oh, look, the mean is far from the empirical average by something. Implicitly, this quantity is saying the same thing, but there is no way to symbolically invert it. But it doesn't matter because I don't have to symbolically invert it. I just want to calculate the interval. So I can invert it numerically. I can just run an algorithm that numerically will construct the interval. And how do I do it? I just have to find the set of all the mu's that satisfy the inequality. And I can do this efficiently because we can prove that it's always an interval. And given that it's always an interval, with binary search, you can find one extreme. With binary search, you can find the other extreme, and you have your interval. Okay? You just have to do it numerically. But there is also another thing, a very nice property. If you use this algorithm, your confidence intervals will never be vacuous, will always be strictly less than 1, even with one sync. Okay? And let me show you that this does happen in practice. So this is a Bernoulli 0.5 random variable, okay? This is number of samples in a log scale. And this is the confidence sets that you construct. So this is the upper and lower confidence sets. And given that this is 0.5, you want these things to converge to 0.5 with number of samples, right? Now, what is the violet line? The violet line is the state of the art on this problem if you want a formula. If you actually care to look at the formula and something that you can actually parse, this is the state of the art. The state of the art is the best asymptotic rate. That's good. Unfortunately, the formula up to, let's say, 80 samples is vacuous. 80 is a lot. Up to 80 samples, this formula is giving you garbage, basically. Now, the red line is my algorithm. And you can see here, I don't know if it is possible. Yeah, you can see here. Look, this is just with one sample. And the interval here, it's already a little bit smaller than 0.1. Already with one sample, you shrink a bit your confidence interval. And so it's never vacuous. And what is this other thing, the black line? The black line is the algorithm by Bowdy, Smith, and Ramdas, the best one in their paper. That, let me remind you, basically says theory will never beat an heuristic. Well, it seems that they were wrong because they are vacuous. Up to 10 samples, they're completely vacuous. And in the middle, they're more or less the same. And asymptotically, it might seem that they get everything correctly. But if we go to a log-log scale, where here there is the confidence width, so how big is your interval, and so you would like this thing to go to 0, you see that they are going to 0, but their rate is completely off. It's not the optimal one, while we get the optimal rate, and we're even as till 10 to the 5, we are still better than the state-of-the-art formula. And by the way, there is code. There is MATLAB code. So if you want to try this thing, it's a very, very simple thing to run. Let me show you also another random variable. This is a beta 1030. And I want to show you this because the variance of this random variable is much smaller than the Bernoulli 0.5. Bernoulli 0.5 has the maximum variance. This is smaller, so this thing is converging to 0, should converge to 0 faster. And this is exactly what's happening because you see this is 10 to the minus 3 here. Instead, this was 10 to the minus 2 for the same number of samples. So this is converging way faster. And again, we have the same things. Never vacuous. We dominate all the algorithms in the small sample regime. Asymptotically, it might seem that they're all the same, but the heuristics are way off, and we are better than the state-of-the-art formula. Okay, so we arrived at the last part, and I might have enough time to actually cover it. So this is the last application that I want to show you. And it's, again, online learning, but to do something that it's not really online learning. So here we will use online betting to prove Bayes bounds. OK, so you had a fantastic tutorial during the summer school by Pierre about Bayes. So I'm not even trying to explain what is Bayes to do. Let's just say that it's an idea that came from David McAllister. And the idea is that you want to construct generalization bounds for a stochastic classifier. Instead of having the usual deterministic one, now your classifier will produce a probability distribution, and you want to understand what is the generalization guarantee of a stochastic classifier with respect to the empirical with its empirical performance, again, with respect to the same distribution. And by the way, I'm trying to, here in these slides, I will try to follow Pierre notation as closely as possible so that you can go back to his slides and you can try to match what's going on. And so this is the classic bound from David McAllister. And by the way, I will also assume, as Pierre did, that everything is bound, all the losses are bound in 0, 1. And so you have that the expected risk with respect to any row, and this is the key thing in Bayes, row can be learned from the data. So the expected risk with respect to any row is less than the empirical risk with respect to the same row, plus a term that depends on the KL divergence between a prior pi, the row, and then a term that depends on the confidence and the number of samples. Now, again, I will use this color-coded Bayes thing So that everything here, all this red part, in a moment will be summarized in one term. The KL will be always green, and the confidence term will be always blue. Okay, so this is the classic bound. What did we prove? We proved this other thing. The red part, that is again, is an expectation with respect to any row of some weird function, where this weird function is this thing, is less than KL and confidence. Okay. Now, what is this thing? This is the same expression that was appearing in the previous part. This is the optimal wealth of a betting algorithm. However, there is a difference here. Now, this thing depends on theta, because the losses, your predictor will depend on theta, and the optimal risk will depend on theta. And so you have this thing for each possible theta. So now you don't have a single betting algorithm. You have an infinite number of betting algorithms, each one parameterized by theta. Okay, so why this is a good bound, why we should care about this weird expression? First of all, you can take this expression here and you can lower bound it with the classic terms from all the pack-based literature. So you can recover McAllister inequality, or you can recover empirical Bernstein pack-based inequality, or you can recover Mauer inequality of Bernoulli random variables, or you can recover unexpected Bernstein inequality. All of them lower bounding the one that I showed you. We basically proved something like a master inequality that it's better than all the others. So you don't need all the others, you just need one. And then if you want to specialize it, if you want something, as a particular one, you can just lower bound it, so make it worse to obtain all the others. If you don't want to do it, by the way, we also show a way in the paper on how to compute numerically confidence interval, but let's not talk about that. Let me show you briefly how you do that thing. So basically, this is what we proved. We proved that with probability 1 minus delta, this ugly expression is less than KL confidence term. How do we do that? One way to do it is that we take log 1 of 1 plus x. This is bigger than x minus x squared. This is the same inequality that I was using in a very, very simple proof of parameter free. It's the same inequality. So I can take each one of these logarithms here. You see that here there are logarithms, and I can lower bound them with x minus x squared. So this term minus the same term squared. And now there is lambda, but there is a maximum over lambda, right? So I can solve the max. And if I solve the max, immediately I get McAllister bound, where the square root comes from the fact that here I have a square. Or by convexity, you can take the same max and you can lower bound it with the small, so-called small KL, where this is basically the KL divergence between a Bernoulli with empirical mean mu hat and mu. And this immediately gives you Mauer's bound. Okay? And why this is important? Because all these bounds that I showed you, numerically, there is not one that dominates all the others. So numerically speaking, in theory, the empirical Bernstein bound should be the best one, but that is true only with an infinite number of simples. With a finite number of simples, typically Mauer's bound is the best one. However, you cannot choose. You cannot really choose which one you pick, because every time you use a concentration, you pay delta. If you pick a concentration and then you don't like it and you want to pick another one, you have to pay another delta. Okay? But instead, if you use our approach, you pay only one delta, because it's one inequality that implies numerically all the others. Okay, how did we prove it? Okay, this is the classic bound. The classic bound is just a change of measure. And you apply the change of measure on the difference between true risk and empirical risk. And so you have true risk, empirical risk, KL divergence, logarithm of this thing with the e to the lambda stuff. And now what you do is that you use Markov. Markov will make delta appear inside the log and will make the expectation of this exponential random variable here. And here, this is the point in which you have to use a concentration inequality to say, look, this thing is actually bounded. I can actually control it. You can use Ofting lemma. And then you also have to tune over lambda in order to get the bound. Now, let me show you instead how we do it. Lambda depends on the data. You already have all the information, basically. If you do the things in the right way, you should not retune lambda. And so we use a betting game again. So you start with welt 1, and you have a betting game for each different theta. So for each different theta, you have a betting game that tells you to bet some money, some fraction money. And the outcome are the empirical losses minus the true risk. This is, again, a random variable between 0 and 1. And so this is your log welt. And you know that if you use universal portfolio, the log welt that you make is far away from the best log welt up to a logarithmic factor. And the optimal log welt is the ugly expression that I showed you before. Okay. And so now let's use this thing. Again, change of measure. But change of measure, instead of using on any function, or instead of using on the difference between empirical and true risk, we use it on this optimal log welt. This is a function, I can still use it. And so change of measure, so we have the expectation of this with respect to rho is less than KL divergence plus logarithm expectation of e to the log welt, optimal log welt. So e to log welt becomes welt. And so e to optimal log welt is optimal welt. How much is optimal welt? Optimal welt is the welt of any online algorithm, A, multiplied by the exp of the regret of the algorithm A, where there is an exp because all the regrets is on log welt, and here I care about welt. Okay. And here is the point in which I get for free the concentration. In the classic proof, I had to use Ofting lemma. Here I get it for free, and I get it for free using Will inequality. Why I get it for free? Because the welt of the probability that the supremum of the welt of any online learning algorithm is bigger than 1 over delta is less than delta. This is Will inequality. Okay, so this is immediate. Where in the classic proof I had to use Ofting lemma to say, oh yeah, this term is controlled. Here, this term is automatically controlled. And so this thing is controlled. And so this thing is controlled. The only thing that I have to control is the regret. The regret, I know that is the regret of universal portfolio. And so that's it. I have that this term, the red term, is less than the KL divergence plus the logarithm of 1 over delta that comes from Will and exp of the regret, exp of the regret of universal portfolio. And that's it. This is the entire proof. Okay, okay, so I'm basically done. I just want to mention other surprising applications of online learning that are out there. These are, by way, not the first times that people use online learning to do something completely different. For example, already in 2008, people use it to prove Rademacher complexity bounds using regret guarantees. There is also a very recent paper by Gergo and Gabor about using online learning to prove Pak-based bounds in a similar way to what I did, but without obtaining better bounds. They just recovered the known bounds using a different way. There is also a very recent archive paper that we have about proving better than KL. You know, KL, it's always appearing in all these Pak-based bounds. We showed that KL is not the right thing. And we showed something even better than KL, uniformly better than KL. And we do it again through online learning. And the last thing that I want to mention, there is a series of paper by Lewis, this guy here, that basically show that it's possible to do sampling in a parameter-free way. And this guy basically visited me at Boston University for a random event. He came to Boston, he was supposed to meet with some guy, the guy was not there, so he started mailing people at random in the department, not to waste the afternoon. And I replied to the mail. And so we met, I explained him all about this coin betting. Then this guy disappeared. And then months later, I saw that he started an entire field about doing sampling with parameter free. And why sampling, by the way? Because there is a connection between sampling and optimization. And you can do optimization in a parameter free way. This means that you can do sampling in a parameter free way. And if you think about it, this means that this guy connected betting with sampling, that I find fascinating. And so that's it. This is a summary of the topics. Thanks for your attention.